which is a part of the Numerical RTA JIP project. A few meeting logistics. There is actually more than 100 participants that have accepted the invite, and I know a lot of you have sent and message that you'll be going in and out of the meeting, but just please, if you're in the Teams meeting, just stay muted when you're not talking, and of course, if you have any questions, feel free to ask the questions either in the Q&A chat box or just on mute if you have anything to say. If you're presenting and you have video easily available, we of course great if you can use or turn the video on. That's just for all of us. We like to see a face connected to some of the content, so that would be great if you could just turn that on when you're presenting. And as I mentioned, the meeting is recorded and will be distributed to the JIP participants only after the call, and also everything, all the content and everything. Just make sure to keep that in the JIP family if we like. When it comes to the update today, I'll give a quick update now from 8 to 9 in terms of, we've been doing a lot of different things. It's a wide audience here today, but what are the highlights of what we've been investigating and researching as a part of the Numerical RTA JIP, and also what is new in terms of the software. And then the main part of the session today is knowledge sharing session related to different topics. So that's different presenters showing different or presenting on different topics. The first one is being a presentation by one of my colleagues, Mo, which will touch upon something that has been requested by many of you actually in the past, and that's how pressure-dependent permeability and also volume beyond the frac tips are impacting the multi-phase RTA workflow. So Mo has kind of then taken feedback from a wide range of you and kind of consolidated it into one presentation and trying to investigate how that impacts the analysis. And then I'm going to get Lucas from Pan American Energy, and he's going to show an example of how they consistently do RTA across different types of analysis. So that's going to be an interesting presentation from Marta. And then Jason will join us for some examples of how they've used the multi-phase flow material balance in the Bakken, before we take another short break and start with the second knowledge sharing session, which will be one presentation by Stephen from Devon on how he has used multi-phase RTA to evaluate refracts, and then I will have a follow-up presentation to that, kind of supporting some of Stephen's observations, just I guess supporting them with some simulation work and some synthetic cases. So that'll be good. After that, we'll take another break, and then the last session is Tyler from Taprock, followed by a presentation from Steve Jones from Simrex, which has actually been a presentation that a lot of you on the call here has requested from many of the companies. Just a way to use flowback data to calculate initial reservoir pressure or initial reservoir pressures. So that's a paper, I think, from 2014 that Steve has presented on there, and it's just a very good paper, and it's a very good topic and very relevant topic for this audience, as the initial reservoir pressure is an important input parameter to RTA. Of course, there's so many activities as a part of the consortium. We have a lot of one-on-one dialogues with each individual company. There is these knowledge sharing sessions, it's the trainings, and there is also a research component to it that we'll talk a little bit about. But that's essentially research that we're working on a wide range of topics that are the topics outlined in the JIP flyer. And all the research, both the good and bad findings, will be provided in a document at the end of the joint industry project. That's what we call a R&D catalog. and also some of the key items will be covered in the JIP course at the project. And if you have any suggestions or special cases that you like to study, that's of course warmly welcome. So just feel free to reach out to us at any point in time if you want to look at, we need to understand this better, or we need to understand, or different ways to model, or what impacts our GOR performance, etc. Like if there's things that you want to investigate or research, but you don't have the time to do it yourself, feel free to reach out to us, and we'll try to find some space for it in this research catalog. So when it comes to the project, there's a lot of participating companies, and the companies have different objectives as well in how RTA can provide value to their day-to-day work. This is the overall list of all the JIP participants, and the goal for the last the last quarter, or this quarter leading up to this session, has just been to get a first iteration of at least 10 wells per companies in the software when it comes to the workflow. There's a few where we haven't been able to finish that, and there's some good reasons for that. And some examples are that they would like to wait additional key samples and validating their models before they run some of these workflows, and that's totally fine. In the next quarter, what the objectives are is to take at least these 10 cases, making sure that we get consistent results, that we also reconcile any potential differences between those results and other forecasting methods internally, and making sure that it's consistent with physical interpretations and whatnot internally when it comes to petrophysics as well. For some of you, there's some companies that literally have thousands of wells in the software at this point, and have done many more than 10 wells. So for those companies that are more off to the races, or there are multiple companies or multiple folks that can do a wide range of workflows, the only objective is to essentially do more cases, do more wells, and trying to provide just value add in day-to-day work. When it comes to the analysis that we're doing on every single well, DVT from equation to state modeling, bottom pressure calculations, we're doing the multi-phase material balance that we'll talk about more today as well, both analytical and numerical RTA, numerical modeling, and for those that are interested, doing the probabilistics and sensitivities. There's a presentation today on the probabilistics piece of this as well, multi-phase RTA. Just a reminder in terms of the scope of work as a part of the JIP, like the main objective of the entire study is to develop best practices and guidelines related to unconventional well performance evaluation. And we think, and we're convinced, that this is something that we investigate better as a community than in silo, and especially when it comes to developing some of these, some consensus around different assumptions, what we're seeing in different basins, and what we can apply cross basin as well. And I think the last knowledge sharing session was a great example of that, where we did a few surveys before the knowledge sharing session and saw that on some things there are a lot of consensus across the different companies, but on other things there's less consensus. So if we can help kind of bridge some of that gap through this industry project, that is already a big win. The other thing is that we of course want to provide a wide range of real examples of the multi-phase RTA workflow. And even though in the actual official project overview, we only count, I guess, 10 wells per company, there's actually at this point been thousands of wells that the different companies have run through either parts of the workflow or the entire workflow. And that has been great to see. And I think just that's probably where and when we apply it to real field data, that we really learn what needs to be improved upon, and what we need to and what really works in general. So on that topic, what we'll provide also as a part of this R&D catalog is essentially almost like a cookie cutter recipe for different observations that you see in the field data. For instance, different types of water cut performance versus time, or GOR performance versus time, that you can essentially have some recipes on how you can match that if you need to do a little bit of tweaking on, for instance, relative permeabilities or different pressure-dependent parameters, etc. There's also this item related to how these different workflows are impacted by items such as well interference, reservoir heterogeneities, multiple fluids from different producing zones, and of course relative permeability assumptions, which was a part of the original scope. Some of these things we can actually generalize for as a part of the workflow itself. For instance, reservoir heterogeneities, that's one of the things we'll talk more about today, but that's essentially what fractional RTA is all about. It's fairly tricky to probably include the multi-fluids in a unique way, at least in the RTA workflow as such. But for those of you who have requested being able to create multi-layer models in Watson Plus, and also be able to actually assign different fluids in the different layers. So you can have black oil and a dry gas, for instance, in the different layers. That's actually possible in the release that comes now on Friday. And I tested it this week, and it's really slick stuff. And the team has done a great job on that. So at least you can either modify your cases from RTA or at least look at how multiple fluids in different layers affect your results and whatnot. And that's also something that we will document in the R&D catalog. Well, interference is a kind of tricky topic to investigate or generalize for in the RTA work per se, because if your offset, bottom on how you draw down your offset files is changing, then your offset boundaries are changing all the time as well. So there we're primarily going for exercises where we include a wide range of models in the same grid, and then we do RTA on the individual wells and what is actually the LFPs and OIPs representing in that case. So that's the exercise we're doing for the well interference problem. The last topic that we're investigating on a research topic is how to consistently account for completion water. And that was one of the clear things in the last meeting that we saw. There's really no consistency or there's no consensus on how we like to account for completion water in our RTA analysis. And many times we see there's this especially big discrepancy early time between the actual produced water, which we believe is from the formation, and the flowback water per se. So that is something that we are investigating, and we're going to provide 2 or 3 different methods in Watson Plus on how you can account or at least include the material balance from the completion job into your RTA models. But that will come probably in Q3 or early Q4. Another thing that we've done, I think probably a little bit beyond the scope of work, has been to compare the methods that we, like the numerical RTA, for instance, to other methods that exist out there: fractional RTA, multi-phase flow material balance, analytical RTA techniques, etc. So that's something we are doing extensively, and actually now you're doing a lot of different workflows and just for one given well that you can compare and contrast against, which is of course very healthy. When it comes to the timeline of our consortium, we're done with Q1, so we had the knowledge sharing session in end of March. Where we're at right now is this Q2 stage. So the session today is kind of finalizing the second quarter, and then the third quarter is to finalize all the proof of concept wells for every single company, and then wrap up the numerical RTA JIP consortium at the end of September. And that knowledge sharing session will actually be a hybrid knowledge sharing session. So if you want to, you can join it in person here in Houston at our offices, or you can join it virtually. So you'll have the option to do. So I just wanted to mention that. And more information about that timing and location and whatnot will be provided in good time. There's different small courses as part of the consortium. We are done with 2 of them. Both are, like all of them, are half day, 4 hours, and they're hands-on when it comes to using both the software and associated theory. So we're done with the 2 first ones. That was on purely PVT parts and purely bottom hole pressure parts. That was in February and April. The next one coming up now is one on RTA specifically. So then we assume our PVT is correct and our bottom pressure is correct, but we're only going to focus on analytical and numerical RTA, and also probably some fractional RTA pieces, which we're, at least on an analytic or from an analytical standpoint, we've included in Whitsun Plus in the release now on Friday. And then there's one on purely multi-phase flow material balance in August. So that'll be exciting. And there's also a final course as a part of the project wrap-up at the end of September. Of course, all of what we're researching, everything that we're doing, whether it's actually applying different proof of concept studies or whether it's or performing proof of concept studies or doing research, in the end of the day, like all that work will not have any value unless we actually can provide it and make it available to all of you in a user-friendly tool. And that's the whole goal with Whitsun Plus. So there's a lot of new technology that you'll see coming into Whitsun Plus in this release this week. For instance, a lot of you have been asking about the opportunities to auto-fit, your LFPs and analytical RTA, so basically a square root of time plot, not only doing it in the front end by clicking, but doing it for multiple wells at the same time. Also, fractional RTA will be included, at least the analytical piece will be included now this week, and then the numerical piece will be included in the August release. And associated to a lot of that, especially for the diagnostic plots, it will now be possible to not only use gas and oil rates specifically, but we also convert the surface rates into reservoir rates. Or you can do it with pure liquid rates to do the to look at the diagnostic plots and how they change there. And that can help in environments where you're producing a lot of water, for instance, or where you have a lot of multi-phase flow effects. What we're really excited about in this release on Friday is this ability that I talked about to perform analysis on wells with multiple layers, both in terms of fluid properties can change layer-wise, and also in terms of petrophysical properties. In the next release in August, you'll also have the opportunity to save cases in the software. So if you have a numerical model run that you would like to save and potentially use again later or rerun later, you can do that, and that functionality will be in both the numerical model and the RTA. A lot of things related to how we can graphically, in a more simplified manner, edit data is also coming in that release, together with the ability to tune your BHP correlation to actual measured data and apply those tune coefficients to all the data set. Will be a detailed communication and video, etc., on this later this week, so we'll just stay tuned for some of that. A lot of the stuff that we are researching, and at least the summaries of that, we like to present and wrap up in papers. Last week at UTEC, we presented 2 papers, Leslie and Barry, that paper that they've written to summarize everything on the multi-phase flow material balance without relative permeability curves, was presented last Wednesday, and that's the method that is in Whitsun Plus and the technology they developed when they were at Cimarex for the last 4 or 5 years they were there. We also presented on how you can, or something we worked a lot on, is how to take numerical RTA and extend it to complex factory systems, so basically what we call fractional RTA. So we presented the first call it version of or the first part of that. The second part, with actual field examples and whatnot, is presented at ATC, also here in Houston in October. But both of these papers can be found in the JIP material. That is, there's the same SharePoint folder that we send out every week, and we've also sent this out a couple of times. But if you want me to send it again, just send me an email and I'll forward it to you. Very good. So any questions at this point, or has there been any questions in the chat, Mo, or is it crystal clear?
No questions in the chat. All good.
Very good. And just for all of you, if you know, at Whitsun.com, there is actually possibilities to request different papers that we've we've written historically. So you can just go into wits.com/publications and actually just click these two, and you can request it, and then we can send these papers to you in that way. Good. So what we're going to talk about now is to switch gears a little bit. Some of you have seen parts of this before, but I think it's really important, at least for us, to make sure that as many as possible have seen the highlights of the new technology that at least we are really excited about, and that we're trying to get into the software, obviously, but also that it's solving what we see as inherent problems with the traditional techniques. As that's the last part of this intro session before we start with the knowledge sharing sessions. So in short, what we've kind of done internally is to have this multi-year deep dive into RTA. So we've looked at a wide range of topics from a wide range of people that publishing papers, or a wide range of companies that have different techniques that they're excited about. And in short, we've found 3 exciting and new technologies that solve something that we consider an inherent problem with traditional techniques. These 3 technologies have all been actually developed by operators. So there's not something that we are pushing at Whitsun, or that someone has invented that because they think it's exciting, but it's actually a problem that is solved by introducing these different techniques. And in short, these 3 different methods are the numerical RTA method from Apache with Braden. This is multi-phase flow material balance from Simrex/Cortera. And it is this fractional RTA from Chevron. So it all comes from operators first and solve a lot of problems. And I think, some of you have seen this before, but I think it's really important to ask ourselves why these needs to be introduced, and just go through each of them and see what problem are they actually addressing. And to really understand what problem they address in short, we need to remind ourselves about the different flow regimes that is relevant for tight unconventionals. It's first and foremost infinite acting flow, which you all know ends as one of the reservoir boundaries. The extreme, which is boundary flow, which starts as a pressure propagation reaches all the reservoir boundaries. And then between that, we have what we call transitional flow, which is this period in between the extremes. We might have seen one of the boundaries, but not all of the boundaries. So this is kind of very, very important basic just to remind all of us about. The second thing is what we can derive from RTA. So we, in general, we for any given well, we don't know how many fractures are actually active, for instance. So we need to know which ones can we uniquely derive if we only have PVT pressures and rates. And that is the A√K parameter, so the so-called linear flow parameter, or LFP, and it's the contacted oil or gas impulse, or the contacted pore volume after completion. But it's also really, really important to remind ourselves, when can we actually observe or derive these parameters? So the A√K parameter, we can only derive or observe during infinite acting linear flow, and the contacted pore volume, we actually need to be in boundary dominated flow. So if we're still in transitional flow or in infinite acting flow, we can't actually say something about the latter part there. And the problem with that is that, and for those who run a lot of models, is if you don't know what your contacted oil or gas in place is, you actually will not be able to say with certainty what your EOR for the well is, because you haven't seen all the boundaries yet. You can say what it at least will be, but you can't say what it would be for sure. And that's a little bit of the tricky part. And if you want to convince yourself that that's true, you can go into Whitsun Plus, for instance, and you can create 10 different cases with the same LFP. The only thing you change is your OIP, and you'll see that the EORs will be higher for the larger pore volume that you have. So very, very important to understand these basics, the flow regimes, and what parameters you can derive. And this stuff we've gone through a little bit before, but I just want to make sure everybody in the call is on the same page before we dive into some of the presentations today, because there's a lot of these topics that, unless you know some of the basics, they're really hard to follow. So I just want to make sure that that's the case. So Numerical RTA, what was the problem we tried to address with introducing numerical RTA? So what did Braden and the folks at Apache that developed this methodology try to solve? And the problem is very easy. A lot of all the analytical models that we have out there in the industry, they assume single phase flow and either a constant rate solution or a constant pressure solution when it comes to resolving physical parameters. In reality, we know we're dealing with both changing rates and changing pressures, which is what we call superposition effects. And we typically drop below the saturation pressure, so we're dealing with multi-phase flow effects as well. And even if you're kind of single phase, you're still producing a lot of water and potentially oil, or vice versa for a gas. So even then, you're dealing with multi-phase flow. So the problem or the way to solve this is to run RTA or do RTA with something that can actually account for superposition and multi-phase flow effects at the same time. And who can do that? Well, we can't do it analytically. That's impossible to do rigorously. But a numerical engine can do it extremely easily. So it's almost like we're delegated everything that's super difficult to a numerical engine. And then we can sit back and do the interpretation part, which we're really good at. And in a nutshell, what you'll see, and I think this is kind of a cartoon of that, is if you do the square root of time plot and you plot points above the bubble point, you get a certain slope. And then when you plot the points below the saturation pressure, you get a deviation from that original straight line. And if you interpret this to be boundary effects, you'll always end up with higher permeability, shorter factor half length, and more wells per section. And you all kind of know the story from there. This is the workflow that was introduced by Braden in this original paper from 2020, and a key diagnostic plot is this LFP versus time plot, or what we call in software in Whitson Plus, and you'll see many examples of that in the knowledge sharing session part of today, is what we call the Bowie diagnostic plot. The Bowie diagnostic plot is basically saying that if your data is flat, so the black line here in the period when it's flat, it indicates infinite acting linear flow, and then deviation below this line represents boundary dominated or transitional flow. The magnitude of the flat line itself indicate the LFP parameter. So this is just the numerical RTA equivalent of the square root of time plot, nothing else than that. And if you really want to put the time to end a linear flow line there, you potentially could. And the nice thing about this is that since you're doing this exercise in real time, you don't have to go through this complicated exercise of converting it from like a material balance time to real time, which is not necessarily trivial. The other thing that you're doing when you're running this methodology is that you're running a wide range of type curves at the same time. So you will try to not only get an LFP, but you're also trying to find the type curve that is closest to actually observed data. So you're picking an LFP and an OIP, or an OJIP if you're dealing with a gas reservoir. And the nice thing about that is that these are the two things that we talked about that you can actually derive from RTA. So now you've done that, and that's exactly the same thing we've always done. So if you've, for instance, taken one of Dave's classes on RTA, you'll see that the LFP or A root K, that comes from a square root of time plot, and then you drag a time to end the linear flow line back and forth, and that is what gives you the oil in place, right? So you've done this before. It's exactly the same exercise. We're just doing it numerical. The inputs to numerical RTA is PVT, production data, which both of, right now we get PVT properties from these field-wide equations of state, unless we actually have PVT data on every single well. Production data is either measured or we can calculate, for instance, bottom pressures from surface data. So it's at least possible to get some estimates of that. But the last thing that is required is relative permeabilities. And relative permeabilities, that's one of the inputs that is not measured, at least I think I've seen 2 rel perm sets ever in shale. And you always have the question, can you actually use them, or how would you use them? and they can't be calculated from readily available data. So this is a problem. And that problem was what the folks at Coursera tried to address with the multi-phase flow material balance technique. And that's the second method that is very new and exciting. So the problem there was simple. All multi-phase flow techniques require rel perms as an input, but in reality, we don't have it. So when Barry or Leslie and Barry, when they in 2020, I think, came to Curtis and I actually up in Oklahoma, and they said, we've developed this new technique that does not require relative permeabilities. It doesn't care about geometry, actually, which is huge for RTA processes or methodologies, and it outputs the contacted oil or gas in place. You know, I remember I was like, okay, this can't be right. So I thought it was complete BS. So Curtis and I, we went back home and we made sure that we we're running a wide range of cases such that we could either show that this either works or it is wrong. And I remember I was kind of like sitting there and I was like, okay, there has to be some simple cases where this method fails. But the problem is for every single case we ran, for all kinds of relative permeability curves, all kinds of fluid systems, all kinds of initializations as well, two-phase saturated, slightly undersaturated, saturated, you name it, complex geometries, more or less complex geometries, with or without pressure-dependent permeabilities, low fracture connectivities, etc. This method, if you give it enough time, it will always give you the correct oil in place and gas in place when you compare it with these simulation cases. So we know this method works now, and we know it doesn't require relative permeabilities. Multiple of the operators that's in this call have tested the method. We've done a lot of that testing. Of course, Coursera has done the testing as well, and now we've applied it for a wide range of field cases as well. So it does not require rel perms, outputs the oil in place and gas in place, does not care about the geometry, which we already mentioned, but it assumes boundary dominated flow. And what does that mean for us in general? Well, it means that if you're still transitional or infinite acting, this methodology will provide you with a lower bound for your oil in place and gas in place when you go into your numerical or analytical RTA processes or workflows. So we use it actively and also with a lot of you to bound our RTA analysis. So we know that whatever this number is, it should at least be that or higher. When you do the plot or interpret this plot, it's very simple on paper. You fit a straight line through a set of data, and the inverse of this straight line is your oil in place, which means that this is a small OIP, this is a big OIP, and this is an even bigger OIP. What can scare some people a little bit about the method is the equation, or the nature of the equation. So the governing equation is this one, and it's kind of, the governing equation for, single phase linear flow, for instance. It has this particular shape, and this is a similar equivalent to that just for this technique. But if you break it down, it's not that scary. It's an intercept, it is material balance time, it is a pore volume, and then this term is mass rate. So it's basically you converted all gas and water into mass, and you just sum them up together, easy. And then this thing is probably the thing that is most abstract for people. It's what we call mixture density, and then mixture density change, actually. Just think about this as any type of density. Think about oil, gas, and water in a tank. You pretend that they're mixed, and you have the whole volume of it, and you also have the mass, and you can compute its density. And you see here that if you multiply mass on both sides, you're actually ending up with something very, very familiar, which is a density equal to mass over volume. The other beautiful thing is that it's a linear type of equation. It's just an AX plus B type of equation, which is very, very user friendly, and is the dream of any engineer. And probably the best part of it is, it deals with a lot of these super, super complex things like nonlinear PVT, superposition, etc., in just a graphical format, and it spits out the correct answer, every single time in general, which just makes it very, very powerful to use. And in general. And we use it all the time, or at least I use it all the time to bound the RTA analysis. Another last point on it is if you see there's big discrepancies between the pore volumes resolved in your multi-phase FMB and what you're getting in, for instance, your numerical RTA workflows, it's another indication that you're either transitional or still infinite acting as well, which is also good output. The last new technology that I guess we're excited about and that solves something inherent is this topic of fractional RTA. And in short, the problem that it addresses is that all classical RTA methods, analytical and numerical, they assume equally spaced fractures. What does that mean in general? It means that any boundary effects we actually observe in real field data, we have to then simplify into one boundary. And we also have to simplify and say we're seeing all of those boundary effects at the same point in time. The problem with that is that in reality, we might be dealing with something that's much more complex, where we see boundaries at different points in time. So we have probably the dominant flow regime in many of these wells is not infinite acting or maybe boundary dominated. It can actually be transitional. And in that case, it might look something like this, or it might look something like this, where we are dealing with uneven frac spacing or what people call fracture swarms. What that ends up with is that you're infinite acting for a period of time. And then you're seeing the first, the first boundary effects, and then you will see other types of later time boundary effects for fractures that are further apart, and that will provide you with this output, which is just a superposition of infinite acting and boundary dominated type of behavior that looks like a power law type of relationship on a log plot, and we'll get back to that. So what I guess Acuna at Chevron did was to provide you with a framework where you could first diagnose whether your system is more homogeneous from a complexity perspective, or if it's more uneven in terms of frac spacings, for instance, or if you're dealing with something more complex. And if you're dealing with something more complex and you would like to model that, he also provides you with the framework of how to take that diagnostic plot and turn it into a more complicated model. And that's what we're going to talk about here for a little bit before we start the knowledge sharing session. So in a nutshell, classical RTA that we've done all the time, we've talked about it here, which is both numerical and analytical. It calls for equally spaced fracture network, where the delta is 0.5. So the LFP there is A root K. Okay, fairly simple. If you think about it, A root K, that's A K to 0.5. And that's what you're solving for in that. Fractional RTA solves for, which is from Jorge here, solves for something that's more complex. So it can be for any value of delta. So then the LFP is A K to the delta, and a delta of 0.5, that's the classical RTA example. So that's just a more flexible framework where the special case is solved for 0.5. And if you have something that's more or less homogeneous, that will just be a value that's between 0.5 and 0. And a delta of 0, that's boundary dominated flow. Okay, so it's just this way to account for that combination of flow regimes, if you like, or the transitional flow regime. So when it comes to your LFP then is A root, or A K to the delta and not A K to 0.5. But except from that, everything else is actually the same when it comes to numerical RTA, and that's the beautiful part. If you want to diagnose what your delta is for a given well, you can just plot the rate normalized pressure on a log plot. That's what you see here. If you think about what rate normalized pressure is in general, that's exactly the same thing that you're plotting on the square root of time plot. The only difference is that your time is not square root of time, is just regular time. And you're plotting just a rate normalized pressure versus regular time on a log plot, and you fit a power law through that, and your delta parameter is this guy right here. And you can also do the inverse exercise if you like to do that, the delta is the same. That's just a pressure normalized rate. Okay, so it's fairly easy to at least on paper be able to diagnose whether this is important or not. And here you can actually run this in Witson Plus in the next release for both total reservoir rates and of course on the single phases, but also on total liquids. So that can be nice in case there's a lot of multi-phase effects and a lot of water and oil, for instance. So when you've diagnosed this delta parameter, for instance, let's say it's 0.3, then probably the elegant part of what they've done at Chevron is that they provide you with this recipe of saying, okay, your delta is 0.3, then I'll provide you with a distribution of single symmetry of element models that has different distance to its closest boundary, such that if I superpose all those models, I get a delta of 0.3. So if you have a delta of 0.3, then essentially that framework provides you with, I'm going to have 60 of this this larger type of symmetry element model, and I'll have 30 of the smallest one, etc. So what does that mean in practice? Well, it means in practice that if you're running 4 different models, of course, seeing boundaries at different points in time, all of these different boundaries will be observed, or the boundary effects in each of the models will be observed at different points in time, and the delta of each individual model is still 0.5. But if we combine them together and we just add all the rates together, we'll end up with something where the delta is not 0.5, and it will look or honor more of a power law type of relationship when we plot it on, for instance, a log, which you saw earlier. Okay, so that's the only thing. So here you don't have to include more. This is just classical diffusion type of concepts with superposition of infinite acting and boundary dominated type of flow regimes. Okay, so it's just a complex geometry, but still classical diffusion type of stuff. So no, we don't need any magical new physics to explain this. What does it mean for our numerical RTA work? Well, for our numerical RTA work, it just means that we still have to have PVT and production data. And the last thing is for the numerical RTA is that we need to introduce a delta. But that's it. And then still you have the rel perms, which still is still a problem, but you can bound that again from your multi-phase FMB. So it doesn't really change numerical RTA a lot. In the software, what you'll see on Friday is that we'll have a fractional version of analytical RTA, so you can do both on a given well, and the numerical that will be in the August release. So that is really exciting. So and of course, all of these techniques either is in Witson Plus or we'll get there in the near future. Very good. Any comments from Curtis or Mo before we take a little break, and then we'll start the knowledge sharing part?
Not specific. It was I think a very good summary and basically emphasis of what we're trying to help provide and make use of ourselves for doing this kind of work.
Sounds good. So we'll take a little break now, and then I'll ask Mo just to start his presentation, and we'll start again at 9 sharp in Houston, which is 8 in Denver and Calgary. And then there will be the first session where Mo will present first, and Lucas, then Jason. Okay, Mom, I think we're getting ready to get started.
Yes, sir. I was just trying to send the file to Scott, but it seems like it doesn't allow me to send it here on the chat. Let's give it the last try. Nope. For some reason it doesn't allow me to send it in the chat. Sorry about that, Scott. So yeah. Let me know when you can see my screen.
Yeah, screen is good.
Awesome. So yeah, my name is Mohammed Dahouk, and many of you know me and have been working. I've been working with most of you, or had the pleasure to work with most of you, I think. So everyone calls me Mo. So if you hear someone talking about Mo, that's me. I will not turn on my camera now because I've been having some issues with my internet connection. So I'm hoping to use all the bandwidth with on the presentation. And if you see that there's a delay on the presentation or anything similar, then just let me know. Just speak out or write it in the chat so I realize that there's some issues with my internet connection. And I apologize for that beforehand. What I'm going to talk about today, as mentioned by Matthias, is two things that are, I think, very important and that have been a result of discussing with many of you. Basically, is how would our RTA, multi-phase RTA workflows be impacted by a well that is experiencing two things. One is the pressure-dependent permeability, so the variation of pressure of permeability with pressure, and the other is the volume outside of the fracture tips. And those we call matrix gamma is the pressure-dependent permeability. That's basically how the pressure the permeability declines with pressure in the simulation model. And the second one is basically this volume that is outside of the fracture tips. How does that impact our workflows? When is this volume important? When can we exclude it, etc. Okay. Before we dive deep into the details of the presentation, just a kind reminder or a quick reminder of since we're going to be talking about how these two things impact our RTA workflows, it's important to remember, again, repeating and stealing Matthias's slide, what we can derive uniquely from RTA. Those are two main things. One of them is the LFP, or the A square root of K, and the other one is the contacted volume, the contacted pore volume, or the oil in place or gas in place. These two things are the only things that we can derive uniquely from RTA, but it's important to also remember that they can be determined at a given point in time of the well's life. So the LFP, you'll be able to observe that during the infinite act and linear flow, while the OIP, you'll only observe it if you have reached boundary dominated flow. So that the contacted pore volume will depend on how much of the boundaries of the reservoirs you have seen. And then the two workflows that we will be talking about is the multi-phase flow and material balance and the numerical RTA. Multi-phase flow and material balance is the method that Matthias covered in the previous presentation very quick. As he mentioned, there's no relative permeabilities that are required for this method. What you get out of it is the contacted pore volume, and it's basically geometry agnostic, and that's something that we will discuss here in this presentation. Basically, the method is plotting your production data, production and pressures, rates and pressures, basically, plotted in a given way where you draw a slope through the data, and that slope is inversely proportional to your contacted pore volume, to your OIP or GIP. And that means that the steeper the slope, the smallest your volume, and the flatter the slope becomes, then the larger the volume becomes. When it comes to the numerical RTA, that's the method developed by Brady and Bowie at Apache, and many of you should be very familiar with this workflow as well. But just a quick reminder that basically, again, what we do is we plot our production data, basically rates and pressures in a certain manner, and we plot that against numerical models that we have run, a given set of numerical models. And once we look at the diagnostic plot, the horizontal flat line indicates that we're in infinite act and linear flow. If we deviate below that line, that represents boundary dominated flow. The value at which the flat line lies, that's your LFP, your linear flow parameter, and the type curve that matches your production data the best, that's your OIP or your OGIP, your gas in place or your oil in place. Okay. That was just a very quick summary. Matthias definitely has covered that many times and much better than I can do. So that was just a quick summary of the workflows that we're going to be talking about here. And then we're going to be working with simulation models, numerical models. And for that, I built a numerical modeling with some plus that has the following input parameters, very basic inputs, an initial GOR of 1500, some initial water saturation of 30%, fractional half length of 400, etc., etc. So these are all the parameters that are there. One important thing about the model is that the fracture half length is equal to the reservoir extent. So that means that there's no volume beyond the frac tip, at least in what I'm calling the base case. Okay, this is the performance basically of that base case. I'm running it for 10 years, and these are the rates and the pressures, GORs, water cuts, etc. Just to kind of as a refresher and a reminder of the workflows, if I took these rates and I tried to run the multi-phase flow and material balance method with this. Before I do that, sorry. So this model has an LFP of 450,000 and an OIP of 3.1 million barrels of oil. If I took this and tried to run it through the multi-phase flow and material balance, this is how it would look like. It's actually a super straight line here. This is straight out to just running the multi-phase flow material balance. This is what you would get in this model. The OIP there is 3,100, 3.1 million basically. So it's very close to what we had in the model. Very accurately predicts that. One thing that we don't see here is the typical shape of the multi-phase flow material balance, that where you have a transitional period, and that's because that's happening very early here in the time of this well. And if I zoomed into this portion here, we would see that shape. You can notice that I go back here, the axis here is 300,000 in the material balance time, and here I'm going to 3,000 just to be able to see that transition. Okay, but even in that early time, I'm able to see that same slope, and with that slope, I'm able to find the OIP, which is basically the OIP that I got from the model. Okay, and as a reminder,
just emphasize, Mo, that it's only the slope that's giving you that OIP.
Yeah, you mean that the intercept doesn't give you the OIP? That's what you mean? Yeah, exactly. That's exactly right. So so the slope is all that matters to give you the OIP. So you could actually have this slope moved up here, and you would still get the same OIP as long as the slope doesn't change. The intercept will not affect your OIP. Very good. Yeah, and this early time period, actually, that's when you're flowing above saturation pressure. So that's when you're still single phase in the reservoir. And this is something that we've discussed in previous sessions, so I'm not going to focus too much on this. It's just a reminder that how the method works and what are the outputs of the method. Okay, this is also now how it would look in the numerical RTA, where you basically, here I'm running 10 models in the background. So I have 10 type curves with different OIPs, and then I have to basically pick the curve that gives me the best OIP, and I have to pick an LFP, and the LFP fairly close to what we had from the model, around 460,000, and the OIP of 3.1 million barrels. So both, what I want to communicate with this is that both the numerical RTA and the multi-phase flow and material balance should give you a very good answer when you're working with this idealized model. Basically, there's no volume beyond the frac tips. There's no pressure dependent permeability, and now we're going to start looking at those cases. So we're going to look at first, we're going to isolate the effect of pressure dependent permeability in the matrix. To do that, we need to introduce this matrix gamma that many of you have worked with. But for those who haven't worked with, what the matrix gamma does is that it's an exponent that will determine how your permeability will decrease with pressure. And what I'm plotting here in the y-axis is the permeability at a given pressure divided by the permeability at the initial reservoir pressure. So here the initial reservoir pressure is 8,000. At that pressure, the permeability is equal to, the ratio is equal to 1. And a ratio of 0.5 means that your permeability has been reduced by half at this pressure. So at 1,000 PSI in this case, we have half of the permeability that we had at initial reservoir pressure. The shape of this curve is controlled by the gamma. The gamma in this case is 1e minus 4. If I increase the gamma, then I get this shape, and the more I increase the gamma, the sharper the drop of permeability with pressure will be. So larger gamma value will mean that you're having a larger drop in permeability with pressure. Most of the people that we have worked with like to work with gamma values between 3 and 4. I would be happy to hear from the audience if you have any experiences with that, if you have maybe worked with larger gamma values than that. That would be very interesting to hear. If you have any comments, feel free to speak or just write it in the chat. So the simulation that we're going to be running now, and we're going to compare that to the base case, is we're going to include a matrix gamma of 4e minus 4, into our model. So we're going to see this type of pressure-dependent permeability shape, and that's what we're going to run our model with, and we're going to compare. We're going to see how our multi-phase workflows, multi-phase RTA workflows, would handle that. Okay, so this is the base case. Just as a reminder, this is the case we started with. And if I include the matrix gamma, then the performance would be the black line that you're seeing here. I'm just keeping the red, like basically what is historical data here is actually the base case without gamma. So here you see what the effect would be of adding the gamma, just adding the gamma on the simulation model. So basically adding the pressure-dependent permeability. And one very key observation is that your GOR becomes suppressed. You definitely will get lower rates, even though here it might seem that the rates are higher, but in QM space they will be lower because there's the period in which the rates are higher. You have a lower rate for the pressure-dependent permeability case versus the base case. But the most important observation is how the GOR gets suppressed, and that's just an important thing to keep in mind. Okay, so now this case where I include the matrix gamma.
Can you just reiterate for clarity, Mo, the green curve and the black curve, which includes the gamma permeability pressure?
Yeah, so the green curve is the base case that doesn't include the gamma. So that's what we have here. And when we include the gamma, then we get this black curve, which is basically the black curve is including pressure-dependent permeability. So green is no pressure-dependent permeability, black is with pressure-dependent permeability, or basically circles are without pressure-dependent permeability, and the black line is with pressure-dependent permeability. Okay.
Just a quick question: if the matrix perm is decreasing, wouldn't you expect the GOR to go up?
No, not necessarily, or not really. Yeah.
I mean, expect is kind of a loaded question. Maybe if you could comment on why you would have suspected. You know, I also just out of the block, knowing nothing, would have thought maybe the same thing. But maybe you could give an explanation of what the logic behind that would have been.
That comment's just based on some simulation work, both internally and with some external folks, where just putting in different values of matrix perm does impact kind of the longer term GOR behavior, and it looked like having a higher matrix perm would lead to kind of a lower GOR late term. So that's why it's just that this is just conflicting a little bit with that body work that I've seen. So that's why.
Okay, you're talking about like a global higher permeability throughout the drainage volume, not connected with pressure.
Well, yeah, specifically in the matrix.
But matrix throughout, but not really pressure dependent, but just having a higher perm versus a lower perm in your block of matrix.
Exactly. Yeah.
So kind of a traditional. What's the effect of permeability in a conventional, or just in a even in a tight unconventional, but if you just have 10 nanodarcies or 1,000 nanodarcies,
Yeah.
you're expecting the higher permeability to have a lower GOR in general.
Yeah. Specifically, we started off with a value of perm that you know, once we ended up getting a more core calibrated model, it increased by, you know, a couple orders of magnitude, and that had a pretty big impact on the GOR behavior.
So I think one of the things maybe others could weigh in on this is that, you know, this matrix pressure dependent permeability is going to have a biggest effect, I think, much closer to the hydraulic fracture, right? A very more localized, you know, kind of like spatially more localized effect on changing permeability, don't you think? Than throughout uniform. Because of much lower pressures near the hydraulic fracture than 100 feet or 200 feet away from.
Mo, this one from the Woolen sir. Can you click that cumulative for the oil rate? It has a crossover at about 1,100 days, but I just want to see what's the cumulative.
Yeah, so the cum you see it here for the base case is 726, and for this case it's 582.
Okay, hold on. 582 is with the pressure dependent perm.
Correct, yeah. And 726 is with without pressure dependent.
Okay.
Just a comment there, Mo. I think one very important impact of including pressure dependent perm in the matrix is if you flip between these two cases, you'll see that the average pressure in the one with pressure dependent perm is much higher than in without. And we know that GOR, at least when you're in boundary dominated, that will have an impact on your GOR as well. So that might also explain some of the differences there. I think that was a question from Rohit as well in the chat here. So is the average reservoir pressure higher in the matrix gamma case? And the answer is yes to that.
Yeah, and Curtis, to your comment on instead of being a uniform decrease in the permeability, something closer to the fractures. I'm reaching back a little bit on an older project, not something I work much anymore, but an old Haynesville project. And I think we're using gamma values similar to this, kind of the mid to the -4, 4 or 5 to the -4. But I remember that being a challenge, and a discrepancy was that didn't want to reduce the matrix perm uniformly in the whole system. It almost seemed like it needed to be more so a pressure dependent skin or change in FCD, something more near the fracture, but directionally agree with what you're saying, something that would have more of an impact where you would think more of the effective stress is changing as you deplete.
Yeah, so I think that's the whole thing, is that, you know, having this pressure dependent permeability is something that's going to have a bigger impact spatially close to hydraulic fracture than throughout the drainage. And not that it's right or wrong, but just the GOR will also be, yeah, I mean, I guess that's, it's not so intuitive, I think, to think one way or the other. Should the GOR go up or go down if you're going to start applying this, let's say, permeability reduction, spatially different places within the drainage void? To me, it's no longer an intuitive kind of like, you know, cause and effect.
The issue, Kurt, is like if you think that you have a reduced permeability and we're controlling the two wells on the same bottom of pressure, right? So the one case with the higher permeability or without pressure dependent permeability, you'll have more depletion in the entire reservoir, whether closer to the frac or away from the frac, but you have more depletion because you have a higher permeability in that case, and I think I would have expected at least a higher GOR in the case in which you have more depletion. Does that make sense? Or
yeah, so I think that everybody just kind of has to think through whether it needs to be intuitive or it is the way it is, which I think is in fact what's being shown here. is that in introducing this pressure-dependent permeability gives you a radically different GOR development over time, which is maybe not what you would necessarily think would be a net result of introducing the pressure-dependent permeability. And I think it is what it is, and understanding it is maybe a longer process, depending who we are.
But I think he's saying the same thing, sorry. Actually, the one that has more depletion with no stress-dependent properties is the one with higher GOR. Higher GOR, sorry.
No, so, and in this case?
Yes, the purple line is from the original case.
Yeah.
No stress dependence, so more depletion in the reservoir and higher GOR.
Yes. That's what I would expect.
So maybe a plot of GOR versus average reservoir pressure, which is the conventional reservoir engineering way of looking at how does the GOR develop with depletion, would make all of this a lot clearer.
I think, yeah, I think we also could, I have some cases that I could, maybe, I mean, it's maybe for the sake of this discussion, it's not a bad idea to show it. So I have some cases that I've run actually for another reason. No pressure dependent permeability for that, but I can show you at least how it looks like. So the difference between each of the cases, is the matrix permeability, and this is in the sensitivities view of that sensitivities module of the numerical model. So you all are used to working with the numerical model here on the history matching. Then we have also this sensitivities module where you can run sensitivities. So what I've done in this case is that I have taken a model and I have changed its permeability from, I think, 2 nanodarcy up to 20,000 nanodarcy, controlling all the time on the same bottom hole pressure without anything else changing. So I can try to quickly show here, maybe, I don't remember the details, but for those of you who haven't worked with this, so basically here you can come and pick which parameters you would like to, which variables you would like to use in the sensitivities. And in this case, I've used matrix permeability and reservoir half length, but I'll ignore the cases with the reservoir half length. So that's, I'm just going to highlight the cases where the matrix permeability is changing. So the cases that I'm showing here are all exactly the same. What's changing is the matrix permeability. So case 1 is the lowest permeability. Case 2 comes after that. It's a bit hard to see here. Maybe, yeah. So see case 7, which has lower perm. Case 5 has lower perm than case 7, but it's higher there. So it seems like there's no clear trend, at least from this. As the case number increases, the matrix permeability increases basically. This is plotting the cumulative GOR for that. Okay, I can remove the historical there. I don't think this clarifies much, but at least it shows that there's no, maybe there's no one answer to this.
But I still think the suggestion from Curtis just for these 2 cases could be good. Mo, just show the the cumulative GOR in association with the cum production as well, and see how they compare. I think Rohit also had a question about why the water cuts are not the same in both cases. and that's just three-phase rel perm effects. So I'll just show the equation that is for. I'll just I've typed the equation for Watercat in the chat there, Robert. So that would just be different PVT and rel perms for the same time. That's the only thing. And Braden has a comment here. With Curtis's comment on it being localized around the fractures, it would behave similarly to a local skin or a low FCD. And a low FCD means that the first reservoir blocks are experiencing a higher pressure than just the downhole flowing pressure. Thus, the lower GOR at higher pressure. So this all makes sense. Yeah, and I would agree to that as well. So.
And that was one of the things we saw way early on before looking at this kind of thing in gas condensate, CGR variation with drawdown in the Motley, for example, that it could be quite variable. Some of those CGRs could follow exactly the flowing bottom hole pressure tightly, that RV curve, and some lay quite a bit higher than that. And one of the physical explanations for that would be an FCD that gave you're effectively seeing a higher inflowing pressure from around the hydraulic fracture than when you have this FCD or this type of effect localized. So the thing is, to me, is that a lot of this GOR variation becomes very not intuitive, at least to myself. But I think these models give you what probably is a standard GOR behavior, cause and effect, without you having to fully understand it to believe it. Eventually, you might understand it as well. So.
Good. Just continue, Mo.
Yep. So now what we're going to do is take this basically case with matrix gamma. So we're going to assume that our production data, our input data, is having the performance of a well that actually has pressure dependent permeability. We're going to take that as an input and make that an input into our workflow and run the workflow. So the first thing we do is we run the multi-phase flow and material balance. There we see in the early time, we see this slope, and that slope actually results in an OIP that is almost half of the actual OIP of the well that early time. So we're basically slower than the base case to see the entire OIP in this case. We see only part of the OIP, at least below the saturation pressure here. Sorry, above the saturation pressure. And once we go below the saturation pressure, I'll just blow up that image there. It would look like this if I zoom out on the plot. And there we have also a slope that we can match in the later time. And that slope, if we see what's the OIP of that slope, it's basically going down the slope, becoming less steep, and getting closer and closer to the actual OIP. And this is after running it for 10 years. And as we remember from what Matthias said, is basically the multi-phase flow material balance method will give you the volume that it has observed, the volume that is actually reached boundary dominated flow. And in the case in which your permeability is lower, you'll expect that takes longer time to reach boundary dominated flow. So that's what we're seeing here. If we give it enough time, it will eventually find the correct volume. But that's one thing that we have to be, or one of the outcomes of using pressure dependent permeability is that you basically will have a slower response in this flow material balance, which means that you'll see less volume early time compared to not having pressure dependent permeability. Okay. And then when it comes to the base case, this matrix gamma case, when we run that through the numerical RTA workflow, what we're going to see, what we see in the the plots is that it's actually not possible to match all the history. As you can see here, you can either match your early time performance, in which case you wouldn't have a very good match of the late time, or you could try to match the late time performance, which gives you a better GOR. I'm going to show that in the next slides. Or anywhere in between, you can try to get like something that matches a little bit the early time, and it's anywhere in between those first two cases, basically. I'm going to show you an example of how that looks like in the numerical RTA workflow. And this is if I ran the numerical RTA workflow without activating the matrix gamma in that workflow. So that's an important observation, basically, or a comment that we're able to tell the numerical RTA workflow that we want to use matrix gamma. And if we do that, we're going to see how the results would look like later on in the presentation. But now I'm just assuming I have no idea that this well is experiencing pressure-dependent permeability, and I'm just running it through the workflow without including pressure-dependent permeability. Okay. In that case, as I said, you wouldn't be able to match the entire history. You'd have to kind of pick. You either, for example, match the early performance, which would be something like this. In this case, the LFP would be fairly close to the LFP of the model, so that to the correct LFP, but your OIP would be half of what it actually should be, or a little more than that. So basically, the OIP would be wrong, the LFP would be almost spot on. One important thing there is that, again, you see that the model, which is this purple line in this case, that's the model with the OIP that I have picked. That model has a GOR that is much higher than the GOR that I'm seeing for this well. So if I picked basically to match the early type performance, I get the correct LFP, not the correct OIP, and my GOR performance. My GOR match is very, very bad. So I'd have to do a lot of adjustments on the relative probabilities to get that. If I, on the other hand, try to match. Sorry? Yeah, okay. I think it was just echo. Very good. So if I tried, on the other hand, to match the late time performance for this exact same well, just using the numerical RTA workflow, then it would look something like this, where you can see here that for the first 1,000 days almost, I'm not getting a good match, but then I eventually matched the later time, and the GOR is matched much better here for that OIP step. The LFP that I would get would be 1/3 of the actual LFP that it should be, so it would be wrong. But actually, the OIP would be correct if I tried to match it late performance. And remember, this is run for 10 years. Okay. That's how it would look like if you went into the workflow and just tried to run the workflow without including pressure-dependent permeability, without telling the numerical RTA runs that you want to include the pressure-dependent permeability in the matrix.
We have a question here from Rohit, Mo. Did you see a flat period in early time that you were able to match?
No, there was no flat period in this case. Here you can see it, Rohit, in the early time. It's just dropping from the very beginning. Yeah. Okay, so the next thing is, okay, what if we actually run the numerical RTA workflow with matrix gamma or pressure-dependent permeability in the matrix? And just quickly to show how that is done in the software, you basically, while you're running the numerical RTA workflow, the matrix gamma is one of the inputs. The pressure-dependent permeability in the matrix and also in the fracture actually is one of the inputs that you can have, and you just provide that and you run, and that will basically give you it will run the base model and all the OIP stems. It will run it with already including pressure-dependent permeability. So how would that look like if we actually run it that way? And it will be a much better match. The LFP 470,000 is fairly close to what we had. We had 450, so that's fairly close, and the OIP is also fairly close. So if you knew which matrix gamma, if you actually use the correct matrix gamma in the numerical RTA workflow, then you should get a fairly good match of the data if the data is exhibiting the behavior of pressure-dependent permeability. Okay. So what are the conclusions of this part when it comes to pressure-dependent permeability? The one of them is that how it affects the multi-phase flow and material balance is that you'll have a delay in observing the contacted OIP, and that's or the contacted pore volume, and that's expected because of the reduction in permeability, and that is translated into a longer infinite acting period. Given sufficient time, that's the beauty of the multi-phase flow and material balance period method. Sorry. Given sufficient time, it will predict the correct OIP if you give it enough time, such that the reservoir or the rates basically reflect that you have reached a boundary dominated flow on your entire contacted volume. If you give it, so if that was the case, if you run it for longer, then it will predict correctly our OIP. And this is one of the cases where it would have been very useful to have buildups, and that's something that I myself have seen also personally in some workflows that I have run for our clients, where you see that when you're looking at the multi-phase flow material balance and you have actually good buildup data, then that buildup data will result in a higher OIP. But that higher OIP, when you take it into the numerical RTA, you're not able to get that higher OIP unless you increase your matrix gamma. So unless you include pressure-dependent permeability. So that has been one of the things that we have found kind of by trial and error. And then when it comes to the numerical RTA, if you don't include the pressure-dependent permeability in the numerical RTA workflow, then you will not be able to match the early and late time performance of the well. If you try to match the early time performance, then you'll get the correct LFP, but you'll not have a good OIP or GOR. And if you try to match the late time performance, then the OIP will be correct, but the LFP will not be the correct one. This is, I guess, back to the discussions that we were having. At least, I think maybe Matthias, you also have worked with a few cases where you have seen the same, but at least in the cases that I have worked on, I've seen a few cases where if the GOR from the model that I'm working with is very high and it requires a lot of adjustments in relative permeability to get it to match with the historical data, then introducing pressure-dependent permeability helps because it pushes that GOR down. Matthias, just feel free to confirm or not confirm.
Yeah.
I haven't seen this. Yeah.
Exactly.
Very good. And now, should I go to the next section, Matthias, or is it time for a quick break?
I think let's just roll on this, and then we'll start with the next presentations after that.
Can I ask one more question before you guys move on?
Yeah.
Any thoughts on when to use fracture versus matrix pressure-dependent perm?
Sorry, can you repeat that? I didn't hear.
So there's a fracture-dependent perm, right? A fracture gamma and a matrix gamma. In the model, do you have any thoughts on when to use the fracture and when to use the matrix gamma and when to use both?
Yeah, that's a good question. I don't have any thoughts at the top of my head, to be honest, like of when to use it at least. Yeah.
I think that's a great probably research topic that we should investigate maybe for the next knowledge sharing session, because you know, yeah, so some people like to keep them the same when they introduce them, and that's probably what they did. And some people like to just keep the one in the fracture 0. Like if you start to introduce it in the fracture, it essentially has a very similar effect to a lower FCD. But I think let's just note that or park that item and make that a investigation item for the next one.
Yeah, makes a lot of sense actually. The one thing that you at least, you know, I think it would be, yeah, maybe most of the times what I have seen when I'm doing the modeling, that's just an observation, not really more than that, is that you'll have definitely a much larger effect when you apply a matrix gamma than when you apply a fracture gamma on your performance. That's the only thing. But more than that, I hadn't actually kind of characterized when it would make sense to use fracture gamma or not, or matrix. And we'll get back to you on hopefully a topic for the next session. Okay, so then the second part of this exercise is or this presentation is to discuss what's the effect of adding volume beyond the frac tips. And this is a very important topic because the numerical RTA workflow is assuming that your fractures are fully penetrating fractures, so they reach the boundary, that basically the reservoir doesn't go beyond the fracture tips. That's the assumption in the numerical RTA workflow, so that will be very interesting to research here. When I talk about volume beyond the fracture tips, I'm talking basically about this green area that you see here. If you had like a model like you see on the screen, then the having no volume beyond the fracture tips would be something like this. If you added the volume beyond the fracture tips, then you get this additional green area here, which you can call the non-stimulated volume, right? Because it's the fracture hasn't reached that volume. And one very important thing to ask ourselves when working with this or when starting to discuss this is when is this non-stimulated volume important? So when does it actually matter? And one thing that we've done is that we took a model with volume beyond the fracture tips. So that's a model that has a reservoir half extent of 800 feet. And we compared it to a model that didn't have volume beyond the fracture tips. And the way we did that, we did it by looking at the cumulative production of the model for different permeabilities. So that's for 2 nanodarcy, 20, 200, 2000, and 20,000 nanodarcy. And this is actually the sensitivity cases that I showed you in the while we were discussing the GORs. Those are the sensitivity cases that I run. So what we're going to do is just look at how does adding the volume beyond the frac tip affect my performance for all these permeability cases. So I have 5 cases at different ranges of permeability. And the results of doing that, as I said, what I used to do that is the numerical modeling Whitson and the sensitivities section of that. So those of you who are interested in learning more about that, just feel free to reach out to Matthias or myself and we can discuss. But yeah, so we ran these cases and then the results are basically what's shown in the screen, where you can see that the first, let's just look at the cumulative oil production, for example. The first column is if you don't have volume beyond the fracture tip, so that's the cumulative production at 1,000 days. And the second column is if you add basically a volume beyond the fracture tip, which is equivalent to the fracture length, actually. So now you have, instead of 400, you have a 400 feet fracture, but you have an 800 feet reservoir half length. So if you do that, the difference in cumulative production at 1,000 days, you see that it increases with the higher permeability, which is expected. The higher the permeability, the more that volume will contribute. But what's important for us is to see, okay, what's the range of permeabilities where it starts to become important, right? And so our conclusions from looking at this, and you can change different things here and study it in different ways. That's why we have the sensitivities module in Wilson Plus. It's basically that if you are in the under the 100 nanodarcy range, it would be reasonable to neglect the non-stimulated rock, the non-stimulated volume, because in this case, for example, we're below at 200 nanodarcy, the difference is 1.3%. Okay. In the 1000 nanodarcy cases where it starts to really matter, and that's why it's important to understand more or less what's your permeability ranges. I think I actually can see here that I think I actually copied the oil table twice, but I can just get that here. Yeah. Okay. So that's when it is important. So I'll make sure to fix the gas table before I send it.
Have you run that case at longer times, let's say after 10 years?
Yes, I have. Yes, I've run it for 10 years actually. Yeah.
Because probably, I don't know, I think the 2120 should always be comparable, I think, perhaps in the 200 nanodarcy at longer times, the difference will increase.
Sorry, I lost you there, Sebastian. Hello?
Yeah, he just said, Mo, that we hear you well. I think that was Sebastian had a little bit of a problem with the connection. But it was basically just a question if you run it for 10,000 days and then just to see the comparison at 10,000 days, basically, for these different cases.
Yeah. Yeah, I think that's a very. I run it for. I think I run it for actually not 10,000 days, but for 10 years, and in the actual cases that I run. So I can add that the comparison at least as a separate table here. That would make sense. You'll see definitely that you'll start to get more contribution the longer time that passes. Yeah. Sebastian, maybe we lost him.
So I think Sebastian is still muted, but just continue, and if Sebastian comes back, there we go.
Yes, thanks.
Yeah, perfect.
Yeah, good. So yeah, so then just we're still using the same base case, and in this case, what we're going to do is basically add volume beyond the frac tip, and if we do that, here again, what's marked in what's green basically is the base case, and what's in black is basically the case with volume beyond the frac tip. So the base case has no volume beyond the frac tips, and the black case has volume beyond the frac tips. So this is what you see. The more rate coming from beyond the volume beyond the frac tips, and also a lower GOR, a lower water cut actually. That may be another item for discussion as well. One important comment here is that this base case, as I showed you in the first slides, it has a matrix permeability of 200 nanodarcy, and this is important for what we discussed here about when does it become important. So we want to show one case at 200 nanodarcy, how does that affect the workflow, and I'm going to also show you a case with a higher permeability, how does that affect the workflow. Okay. So if I take the case into the multi-phase flow and material balance method, I see actually a fairly straight line here, and the OIP of this is basically equal to the stimulated OIP. So it results in an OIP of 3100. So it basically sees all the volume between the fracts, but nothing beyond the frac tips. Okay, and this is for the simulation period that I'm running now, which is for 10 years at 200 nanodarcy. Okay, as we've discussed before, the multi-phase flow material balance, if you ran this for sufficient time such that volume beyond the frac tips had become in boundary dominated flow, then it would have been seen by the multi-phase flow material balance. But that's not the case, at least here. So here it will only see that interfrac region volume. So that's the stimulated volume. If I run it through the numerical RTA, then here I also, in the numerical RTA, I'm not able to, there's no option in the numerical RTA to activate to say include volume beyond the frac tip. So it's always assuming that your fracture is fully penetrating. And in this case, I get an LFP of 470 and an OIP of 3145, which is actually equal. The OIP is equal to the stimulated OIP. The LFP is also the same as the LFP of the model. So we get a very good LFP, and the OIP that we get is actually equal to the OIP of the stimulated volume. And since we saw, and the reason for this, just to double, to show again, and this is running it for 10 years, that if you are in this range, like in the 200 nanodarcy range, that volume beyond the frac tip will not have a large impact. One thing that you can do in the software, just as a side comment here, one thing that you can do in the software if you want is after you have resolved the parameters of the stimulated volume, because you have the correct LFP, but you have the OIP that corresponds only to the stimulated volume, you can, if you want to just do it for the sake of forecasting into in 30 years, you can include volume beyond the frac tip in the numerical model after you have resolved the LFP and the OIP from it. So that's and that's something that a few people do actually. Any questions, Matthias, in the chat? Or?
A few in the chat, but I think we can answer those just in the chat. I think they're actually related to the pressure dependent perm questions.
Okay, can get back to that also later if we have time at the end of the session, at the end of the knowledge sharing session as well. Okay, good. So this is showing that okay, if you are in that 200 nanodarcy range, then the method will, the workflows that we're using should be fairly okay at giving you the stimulated volume, at least give you the correct LFP, and that should be actually all you need for modeling these wells, because there's no impact of the volume beyond the frac tip. If we went to a case where we make the reservoir the matrix permeability 2000 nanodarcy now, okay, so this case is 2000 nanodarcy, where the extent of the reservoir is 400 feet, and that's equal to the fracture half length. So here, this is a fully penetrating fracture. The permeability is 2000 nanodarcy, which is fairly high. So you see very quick, super quick depletion of the reservoir here, and you see also very quick decline of the rates. If we took this case, which is 2000 nanodarcy, and now added volume beyond the frac tip, there we'll see that the rates will be different when we add the volume beyond the frac tip. Now the black case is the volume beyond the frac tip, and the green case is without volume beyond the frac tip. Okay, so that's the difference between those. And now we're talking about the 2000 nanodarcy case, where you expect that volume beyond the frac tip to start contributing. This is just the same plot in Cume space, and I just realized now that this would have been good to show for all the previous ones. So that's a lesson for next time. But basically, this is the difference between the production at for this model at 2000 nanodarcy. The black line is with volume beyond the frac tip, and the green line is without. Okay. And here you see also GOR, water cut, etc. Awesome. So if I took this this data with volume beyond the frac tip and 2000 nanodarcy into the workflows, then first I take it through the multi-phase flow and material balance workflow, and here I get this slope, which is corresponding to an OIP of 4.7 million, which is larger than the stimulated volume, but less than the actual volume. So this is just as much of the volume that has reached boundary dominated, that has become boundary dominated. Okay, that's what you will see here. So it's not it's still not all the volume is boundary dominated, but since there's so much contribution from the non-stimulated rock, then you end up with a higher OIP than the stimulated one. And when it comes to the numerical RTA, then we get something like what's shown in the screen, and the LFP is also higher than the stimulated LFP, and the OIP is higher than the stimulated but less than the actual. That at least I think I can make sense out of this, because basically in this case we're assuming in the numerical RTA that the fracture is fully penetrating, and in that case we're basically trying to get we're getting a larger volume than actually stimulated, but that's just because there's so much contribution from beyond the frac tips that has to be accounted for in some way or form. Okay, so for this section, what are the conclusions? So if we are in the 100 nanodarcy range, it would be reasonable to neglect the volume beyond the frac tips, that non-stimulated rock volume, because the results should be within 5% in terms of cumulative production. If you get to the 1000 nanodarcy range, it starts to really matter. So it's important to understand the permeability in your area. And this is just what we showed in those slides, like the cumulative production for different permeabilities. When it comes to the multi-phase flow and material balance, as mentioned many times, this method will only capture whatever volume of the reservoir that has reached boundary dominated. So because it assumes boundary dominated flow. So in the cases in the 100 nanodarcy range, the multi-phase flow and material balance will result in your stimulated volume, which is good. In the case of 1000 nanodarcy and above, it will result in a volume that's larger than the stimulated volume, because it will just result in whatever volume has reached boundary, has become boundary dominated. And definitely, if you give it sufficient time, it will manage to resolve the entire volume. For the numerical RTA, in the 100 nanodarcy range, and it will result in the stimulated volume and correctly predict most of the historical performance, which is also good. And if you are above 1000 nanodarcy, then the numerical RTA will compensate with both the LFP and the OIP being larger than the stimulated volume, because the model itself doesn't account for volume beyond the frac tips. And that's it. I realized it was a very long presentation with lots of questions. So thank you for the patience, everyone.
Great. So I think there was a lot of questions during the talk, so that was perfect. And there's also been a topic that's been requested, and we've talked with tons of the companies and the RTA, JIP about these two things and how it affects the workflow as well. So it's very good that you went through that, Mo, kind of for all of us. I think what we'll do now, we'll take a 15-minute break, and then if Lucas can share his screen, and then we'll start with his presentation just off the break. So we'll be back in 14 minutes and restart at that point.
Thank you very much.
Okay, great.
Looks great. And is your sound working okay, Lucas?
Yes, I think it's working.
Perfect. So we'll just get back again in 13 minutes, and that's
Okay, great.
great. Perfect. Hey, Manuel. I have a short break here, and we'll be back in 8 minutes.
Great. Yeah, I had a meeting from 9 to 10, so.
No worries. No worries.
Apparently, I missed some really exciting stuff, according to my colleague Misha. He's slacking me screenshots.
That's good. There's a lot of good questions as well. Whole, yeah. It's a very good session.
So that's exciting. You have the new release coming up on Friday.
Yeah, that's we have multi-layer and a bunch of cool things. So
Awesome.
yeah, dedicated email and like a little software tour with the features and everything. So that'll be exciting.
Awesome.
Hey, Joe. We have a short break here. We'll be back in 5 minutes, and then we'll start the next presentation.
Very good.
Great. So we'll just continue and get started with the next presentation. So in this part, it's going to be Lucas who will be presenting, and then it's going to be Jason from Whiting after that, before Stephen from Devon will join us on a few items. So this presentation will essentially be a presentation from Lucas. He's with Pan American, joining us from Buenos Aires, I think, Lucas, correct?
Yes. Yes.
And has been doing some very good work on this, and we're looking forward to your presentation.
Okay. Thank you, Matthias. Well, so idea I make a quick presentation to show you how we look for the consistency across different RTA analyses, and that for us is really crucial. So now, so basically, for any reservoir engineer, the UR prediction is a really tough moment. Even it's really important in the early time of the well, since in our case we are just in Vaca Muerta. We don't have so much information. We have like few wells for each area, so it's really crucial to have a really good interpretation of the UR. So, and also this is really tough since we don't have enough information of the unconventionals generally, and we are also dealing with the early time. So in what we like to use is something that is also in the workflow, that in the Whitson workflow, that we estimate EURs in different ways, in different methods, like in first DCA to perform something more conservative, then go to the RTA analytical, and later to the numerical RTA. We also did this in other softwares, but it's really good that we have everything here together. So to start, we start with the definition, with the PVT definition. Here in the area, we have a black oil with a really high initial reservoir pressure, like 9,500 PCA, around that value. And it's a really luckily, well, it's a low GOR, like around 280 standard barrels per barrel. And then we start with the DCA. Here we generally use the modified hyperbolic in order to have a more conservative decline. With the new tools in the Whitson, it is quite easy to define a final B in order to estimate an UR. And well, playing a little bit, we found, take this out. Our EUR here is around 1,400 million standard barrels. And the thing is, this workflow that we use, we are generally didn't do it every year, or even more often as well, in order to be consistent. And since this is going later on into our reserves book, so it's really important for us. So okay, later on we have in order to keep going to the analytical and numerical, we calculate the bottom hole pressures. In this case, since our bubble point pressure is really low, it's around 1,800 PCI or even less. We select the Hagen and Brown. In this case, most of them will be fine. And before going to the analytical, we perform the flowing material balance, and in the flowing material balance, we start selecting different slope. Here, just a section of the plot, and also, so we start defining the original slope. And let me use the pointer. So here we have in the original, we obtain an estimate original oil in place, and later on also we check that our average pressure is above our flowing pressure. Also here our flowing pressure is above our average pressure, but that's okay because we have an event of frag hit from another well that was like 800 meters away. But later on the well keeps with the trend quickly, so we overlook that completely. Okay, so after that we go to the analytical RTA. This analytical RTA, again, we identify the main objective here is to identify the linear flow parameter and the end of linear flow. So in order to once we go to the work to keep going with the workflow, we compare with the numerical as well. So going to the numerical, in the numerical RTA we input by our flowing material balance original or in place. In this case, 8,500 million standard barrels, and then we look for the best LSP, and in this case, our linear flow parameter is way above the one from the analytical, but it's a check that we need to do, and we find a good or more or less good match in the Bowie diagnostic plot. Also, we start defining we define our well physical assumptions. Once we have these assumptions, we start working in the numerical model. We send this with export option and send it to our numerical model. As we can see in the history, we have a pretty decent match. It's really good. We have this using as well control. We like to use the pressure as well control, since our gas rate or oil rates sometimes they are not so accurate. So we always like to use so we have our pressures compared to the bottom-hole pressures. And after that, using the new capabilities of the software, we use the forecast. And in this case, we define, sorry, it's a little bit small, but trust me, it's around 10,000 days. It's generally what we use, around 30 years or more, a little more, to generate our curves, decline curves. And we define a decline of 20% per year, just to obtain a decline pressure in order to be defined, and then we obtain finally our new EUR in this case. So also I haven't mentioned, but we use the unconsolidated, for us it's the consolidation, the person-dependent permeability. For us is also really important. It helps us not to overestimate. Sometimes working with early stage data, it could lead us to oversize all the capabilities of the well. So for us, it's really important to keep it conservative and to keep it real. And in this case, our EUR it is a little bit lower than the DCA, so it's around 1.2 million standard barrels. And for us, is quite okay, since in other softwares we obtain similar values as well. So we're really happy with this value. So more or less, this is what we do every single well. That for us is also really important, in order to then, if we're going to create our type curves for each of the areas, that will help us to define the potential of each area. So by this we generate like a common process in order to unify this workflow. And if in this case we have a really complete different values, we always go back to the DCA, redo the DCA analysis with other look, and also always try to rework it in order to have a similar values like here. That is really important for us to be on the same level. So I think I went a little bit too fast, but it's more or less what we want to show you. This everything is integrated in the tool that is really useful. We can keep going with other wells, and I hope next time we can see even more applications. So it's really good.
Very good. Just if you can just go back a couple of slides there, Lucas. Just I think one thing that a lot of people, when they look at especially the GOR data there, that the GOR data is a little bit noisy. We've talked about that a lot. Like, this is definitely an undersaturated system, and it produces above the bubble point for probably years, actually, which is a kind of a cool thing about Vaca Muerta, that you're probably the closest thing you'll get to a single phase oil system in unconventionals. But can you just give a couple of comments about what compares the noise in GOR?
Well, this is here. The noise in GOR is definitely due to it's a little bit of the information is not really accurate. As I was saying, our gas production here maybe it's not the best way to estimate this, since we don't have any correct measurements, but since it is so low, for the moment we don't have any more quality data for these cases. And as you say, in this area, we are for a long time we are still above the bubble pressure, so we don't have this change in the production. So yes, also it happened the same with the water production rate here is really low. So it's also helped us to be only, so at the in a couple of months to be only oil producers, and that's what we all want actually. So
yeah, right.
Yeah.
And then just if you go back to the multi-phase flow material balance plot is there. Really likes the fact that you highlighted that this is kind of a bash or a little bash or bracket, such that you're not violating a potential buildup there, which is really good to see as well. When it comes to the values that you used for pressure dependent perm there, the 4 values, you have the same in matrix and fracture, and that was also a question we had earlier. Was that just to be consistent, or was that something you've used other places, or?
Generally use it in order to be consistent, but we don't have that much data in order to be selective of which one we should use. So we use it like a tandem to work it both together. But as you can see, as Mo was showing in the example, for us it's something, and I also use these values similar to these values in other softwares like Topaz for numerical RTA as well, and it works quite good.
Great. Very good, and thanks for sharing this, Lucas. Just due to time, I think we'll go to the next presenter now, and if there's any questions to Lucas, I'm sure you can reach out to him directly as well. Next up now is Jason from Whiting.
Sure. Thank you. Bye.
Thank you, Lucas. Are you there with us, Jason?
Yeah, I'm trying to turn on my camera. Hold on. There we go.
Perfect.
All right. And share that one. All right. Looking good.
Looks very good. So just for everyone who doesn't know Jason, he's with Whiting. Did I pronounce that correct? He's been a good at helping me to pronounce different words correctly. That's that's how we built our friendship, Jason.
Yeah, that's one of my gifts. Teaching.
Exactly.
I lived in Norway for a while, so
yeah, that's another way we've bonded. But you've also worked in with a lot of the folks here. Like you were with Cimerex for a period of time, so probably some folks.
Cimerex for about a year, but most of my career with ConocoPhillips, the vast majority, and been with Whiting, I guess 4 years this week. So it's been, and I guess Whiting will be around for at least one more day. We'll probably close our merger the end of this week. So anyway.
With Oasis for those.
With Oasis, yeah. Exciting times here at Whiting.
Yeah. Cool. I'll just go ahead and mute myself, Jason, and then I'll leave the floor to you.
Cool. Yeah, so I'll just go over some stuff we've done kind of recently with the multi-phase flowing material balance on some of our Williston assets. So see if I can get it to go. Yeah, okay, it's a little sticky here. So anyway, so I applied the multi-phase flowing material balance as part of a to better understand a completion kind of uplift test that we did on some of our assets. The setup of the completion test is pretty straightforward. So we have 2 DSUs. I assume you can see my cursor. So DSU A has 3 new wells drilled in it. Kind of got our base completion. And then about a mile away, we have DSU B. It has 2 wells drilled in it, new wells drilled in it. And it got about a 40% larger completion, both in terms of sand per foot and in terms of liquid pump per foot. And then each DSU has a parent well that's at least a decade old, and all these wells target the middle Bakkens. There's no multi-zone going after multi-zone here. It's middle Bakken only. So that's kind of the setup of the test. So 2 DSUs fairly close together, assuming that and we think the geology is fairly similar. And then a set of wells got 40% larger completions. And again, each well sort of averaged the same. So it's not like, the average of these, they're all 1.4 times, and these are all base. So there's no, we tried to get the same sort of completion on each of the DSU-A wells and the same completion on DSU-B wells. There's no like averaging going on between those, if that makes sense. So one of the reasons I want to try it out here is after hearing the talks from Leslie and Barry, I was very interested in trying this method. This is one of the first places I tried it out. And that's because it's basically fairly, undepleted. We think this area is fairly undepleted. We have a large amount of headspace until we get to saturation pressure. So what I was hoping was that I'd sort of get that early time OIP, like they showed from their paper on that Eagleford well. They kind of showed a early time OIP, and hey, that matches what we're seeing in late time. So that was kind of the idea. So on the left here, I just have the phase envelope. You can see we think the pressure is fairly high. And then, coming down, we have plenty of headspace to try to get that before we're going to have the GOR start increasing on us. So that's one reason I wanted to apply that to this area. The other one was that the typical artificial lift strategy out here is to flow the wells up the frac string or velocity string for a period of time, and then run an ESP. So all of the wells on DSU-A and DSU-B had velocity strings run on them. And so that's kind of this green box in time. So about 60 days. As part of that, we ran memory gauges on all those velocity strings. So we have, measured data here during the velocity string. And then obviously when we put in the ESPs, we also have measured data for there. And luckily none of the gauges died on us. So that was a win. So essentially, I have measured data for the entirety well life, at least so far, at least until we go to rods, then that'll probably stop. But so far I have about a year, a little more than a year at this point, pressure data, measured pressure data. I was really glad that we had the pressure data for all this, because originally DSU-B was planned for 3 wells. Again, that's the DSU that only got 2 wells drilled. I don't quite know the reason why the asset team changed that, but it did only get 2 wells, but the facilities were already sized and built for 3. And so due to these wells also producing a lot more water than the team was expecting, essentially DSU-B with the 2 wells had very little facility constraints, because again, they thought the facilities were designed for an additional well. And DSU-A with the 3 wells, they did see some facility constraints. So, it was really good to have this pressure data to sort of better understand the production volumes. And so really the deck was stacked, and maybe the asset team planned this, but the deck was stacked for DSU-B. They had 40% larger completions. They had a wider well spacing with only having 2 versus 3 wells, and essentially very minimal facility constraints relative to the kind of control DSU-A wells. So anyway, I think that's all I have for that one. And then, so this slide kind of summarizes the OIP estimates I made with the multi-phase Whitson Plus / Cimarex analysis. One of the things I like to sort of get feedback from the guys that have done this a lot more than I have is I kind of what I call like aggressive slope picking, and so here, this is one of the wells here. I guess it's well A2. I basically went in and I looked at sort of what's the most OIP I can kind of justify. And I guess there was a couple of reasons why I went that way. Was I was thinking, well, it's early time and it's sort of a minimum, so I kind of want to get the maximum minimum, if you will. And then also these OIPs, I guess, thinking back today, are also kind of more jived with what we're thinking from our decline curve analysis type deal. So I guess those are two of the reasons, but obviously if you look over here on, so this is the pressure for that same well, I'm like, yeah, I noticed a lot of the presentations today, they kind of more hug pretty tightly to the bottom hole pressure, where I didn't worry about that as much. Maybe I should. Anyway, any feedback on that would be appreciated. And so the table down here in the lower left basically have the OIP estimates for each well. And I feel like they're compared because, again, I tried this aggressive slope picking for all of them. So if nothing else, they're comparable, maybe not accurate, but definitely I was going for comparable. And essentially what we're seeing is there's, you know, we're not seeing a whole lot of difference in the OIP. Between the wells that got our base completion versus the wells that got 40% uplift. Actually, if you average them, I think the ones with the base one have slightly larger OIP per foot. But anyway, I think that's more within the resolution of the tool. But what I did find fairly good was I could get OIP estimates this is kind of in the 150-day range was kind of where I was getting these picked by. And so that's, you know, fairly early time, which is nice. And I felt fairly confident in, you know, that they're in the ballpark anyway of OIPs, where I can't say I've had that feeling with other softwares, where it's kind of like the OIP or the flowing material balance was kind of what I did at the end just to make sure, hey, nothing looks really weird. Can I get it in the ballpark? Where this one, I'm actually doing the opposite. I feel fairly comfortable with these OIPs and actually using them to go in and sort of guide my XF, you know, so kind of this is the beginning of the workflow. And I have to, because of the saturation differences in this area between some wetter zones below us, I'm having to do this in a multi-layer model. So I'm basically, my workflow for this particular project was to kind of get the OIP estimate out from Whitson from this process, and then take that and kind of guide my XF in the multi-layer model. So in conclusion, you know, I think I feel like I'm getting fairly reasonable early time OIPs estimates from this analysis. So that was good. Good job, Cimerex, on coming up with this. I think you have a winner, at least for us. Again, this was, in my mind, kind of a pretty, you know, easy place, if you will, to apply it. So I was hoping it would give me some good results, and I think it did. I didn't show any production volumes today, but, you know, the limited difference in OIP kind of concurs with what we're seeing from the production data that we have for these wells. So that's not inconsistent with that. And therefore, I think the small difference in contacted OIP between these two completion size is more, you know, probably, you know, is the bigger completion may be a little better, but it's probably within, you know, the resolution of either the tool or our allocated data, which is always the issue. And also, yeah, sorry, the point of the FMB obviously accounts for the drawdown differences. So, you know, it's really important to highlight to my management that, hey, this would have been maybe a different story if we didn't have the pressure data on this. And so that's kind of the conclusions on the FMB analysis, little software nice to haves, if you will. And I've already communicated these to Matthias, but I figured, hey, just throw it out to the broader audience as well. The ability to save or type in the OIP and sort of see the corresponding slope would be nice to do, because it's, I don't know, for you guys that have used this, you know, having a little hand at the end of the stick of the line, it can get a little, like you move it a little bit, and in some cases it can change a lot. So that would be a nice to have. Also kind of save multiple cases, so I can have my aggressive case that I talked about, maybe more like, here's what it is if I sort of fit it through, you know, as much data as I can, and here's kind of a minimum or something. Anyway, so a similar functionality as the decline curve panel, kind of have a save as for those different slopes. And then I know the multi-layer model is coming, so I'm excited about that. And I guess it's what, tomorrow or this week, which is great because right now I'm basically having to build out these wells in 2 different softwares, which is not fun, and obviously not very time efficient either. But it's, yeah, like I said, I'm fairly impressed with the OIP estimates I'm getting, so I'm continuing to do this on other wells. And that's all I have on that. Let's see if I can see that.
Great, thanks, Jason. Just a couple of comments on while we're at this slide. That's great. So the multi-layer is in the next release now on Friday, and the ability to save cases not only in multi-phase FMB but numerical models and history matching and stuff is coming in the August release. And I talked to one colleague after you mentioned this ability to type in OIP and then the slope will change. And he told me that will take him 2 hours. So apparently that's just across, that'll be a hot fix before August. So we'll get that in there as well. So that is a very, very good feature request. I also have one comment just on your, you talked about a lot of the cases we saw today, the average pressure and the bottom of pressure curve, they were kind of hugging a lot in the cases. And I think that's just due to the tank sizes in those cases were probably small. So there's nothing wrong with that. It just indicates that you have, call it a bigger tank. So nothing to worry about on that. So just for the audience, if you can just flip back 2 slides there, Jason.
Yeah.
Great. This one exactly. That in some cases that we looked at, the difference between the black line and the gray line has been smaller, but there's nothing wrong with having a difference like this at all.
Okay. Yeah. Good to know. Good to know. And this little bump here, that's a ESP change out. That's that gap there basically.
Yeah.
For those.
Yeah, Jason, a quick question. How did you compare with the volumetric calculation from the map, or you cross-check with the geologist? How does it compare?
Yeah, I haven't looked at it's not too bad. It's fairly close. Again, let me think. It's been a while. Let's see. It wasn't as bad as I know Braden and a few others in the Permian were having some, fairly big differences. I can't remember off the top of my head, but it was, again, with these sort of aggressive, I don't know if that's, aggressive slopes. I was getting fairly, it was under, but it wasn't significantly under. Like it was a smaller OIP, kind of per section, but not, if we went in there with the number of wells we're thinking, we'd still be sort of under the OIP that the geologists are estimating in there. So they're fairly consistent. Again, we have a lot of advantages here in the Bakken being a fairly simple system relative to what some of you guys are dealing with. So, which is,
Yeah. Curtis, you have a comment, question?
Yeah, thanks, Jason, very much for the presentation. I had a couple of questions. You had bottom hole pressures, reliable bottom hole pressures for all these wells, which is great. I'm just curious, this is pretty much just a oil water system, right?
Yeah, and then until we get to bubble,
it's above bubble point.
But in this, we're starting to see here, this is starting to trend up. I don't think we've depleted the whole reservoir. I think there's probably higher perm streaks versus not as high perm streaks, but anyway. That's
I guess what I'm curious about is how reliable did you go and check calculated bottom hole pressures versus your measured bottom hole pressures, just kind of where you don't have that kind of data, how your comfort level in using those for these wells, that you had the data. I mean, did you go and check, Hagen and Brown or this or that and see what correlation, if any, does a better job or is doing a good job?
Yeah, I mean, I generally use the Hagedorn and Brown or the one that starts with the W and the G, or the G and the W. I don't find that I get a whole lot of difference between the ones that are kind of specified to oil. But no, I haven't done like a exhaustive look at actuals. Actually, this is one of the first wells, or one of the first areas that I said, hey, let's, if you're going to run a velocity string, let's get some data. So, but yeah, I need to probably look into that and sort of say, okay, we're going to standardize on, we'll always use X. Generally, I've used Hagedorn and Brown with the, with the other software. But I find that I can't remember the name of the correlation, but it's the one that has a very long W name and a G name. Sorry,
Yeah.
Voldemort and Gaillard.
Yeah, there you go. See, you help me pronounce things as well. So
yeah, exactly.
It's a two-way street. Yes.
Think about Voldemort and Harry Potter, and you'll get there.
Okay, there we go.
The Voldemort.
So then I had one other question, if it's not going to take up too much time. Did you study kind of a what if? How would those? You selected these wells because you knew you were above the bubble point for a significant chunk of time.
Yes.
Did you try to run a case where you just drew it down much harder and faster, and then tried to analyze the simulated results in terms of the flowing material balance to see how much did I lose there, or how much advantage did I have by? See what I'm saying?
Yeah, no, I haven't done any simulated cases, but that's a good idea to try out. So you're saying draw it down faster and just see sort of.
Do you lose some of this character on choosing the slope that's consistent with, in that case, of course, you know the answer from the model.
Gotcha.
And it sounds like, if I remember right, Leslie or Barry had when they mentioned this about picking some of the wells where they had single phase flow early on, and they really tried to use that. That it was kind of a key finding they had, that if you lost that, then you could get lost in some of this multi-phase, three-phase behavior. So I was just
you're saying how long would this area simulated, how am I losing the single phase sooner? How off can I be, I guess? Or
kind of
no, I haven't done that, but I can definitely try. I guess I was pretty excited that this was showing me a while in
exactly
in single phase or whatever, the undersaturated phase, which is what I was expecting. And the data only gets worse from here, so I am going to try to apply this on older wells in this area, but generally I won't have that velocity string / frac string pressure data, but once the ESP kicks on. So I generally don't like that data anyway, so anyway.
Okay.
That's a good idea to try to do some simulated cases.
Great. No, perfect. Great question. So actually, one of Curtis's questions was the same as Rohit had. I had a question if you'd ever tried to compare the BHP correlations with these gauge pressures. So that's already covered. Daniel had a very interesting question in my opinion. So he's wondering if your larger fracs are targeting a higher OIP or just accelerated production or both. And he's curious if you could achieve accelerated production value with larger fractures, but missing it in looking at an OIP. And,
no, I think that's possible. So the wells with larger fracs, again, I didn't show any production volume data, but they do produce more. It's not significantly more than, but they do have a higher cum. If you just looked at straight up cum, I don't care about anything else, or even if you pressure normalized it, the bigger frac. So there may be an acceleration piece. It's not overly significant. It's kind of in the ballpark of, again, we're sort of sub 10%, 5 to 10% sort of increase if you kind of just look straight up the volumes, and then but when you're pumping 40% more sand and liquid, it's starting to become a economics question or whatever on that part. But yeah, there's a possibility of just some acceleration, yes, but is it enough, I guess, is what we're wrestling with. But that's a good point.
Perfect. And then he was also kind of on that, if you got some LFP parameters just for these wells, and if that was kind of apparent in the LFP parameter.
So I didn't. So I guess that's, again, goes back to the multi-layer model. So because a lot of our frac is going into a pretty wet zone, most likely, like because of the amount of, I think it's because of the amount of liquid per foot, we're getting pretty high height growths. I don't, on this particular one, I literally just use OIP for these wells so far, because I can't get anywhere close to the water, and I can't like average my way into a single box. So the SWs are like, you know, target zones maybe 30%, the wet zone's more like 70. And so, you know, if you try to average that to 50 or 55, you know, the single box just doesn't work. So that's, again, that's the reason I went to the multi-phase, so I can get those two distinct reservoir properties. That makes sense. And then I estimate my LFP from that multi-phase again. So using from this work, I use sort of get my idea of contacted OIP and then XF in the sort of the, you know, I don't think the oil in the wet zone is very movable. And so I'm basically sort of using this to get an idea of XF for those wells, if that makes sense, and then calculating the LFP from the multi-layer model in another software that's, you know, has a green tinge to it.
Sounds great. And the last question is from Yoshi on did you ever like bring any of the OIPs into like a recovery factor calculation, and was there any differences in the recovery factors that, you know?
Yeah, so that was more done in the, again, in the multi-phase simulation. Yeah, I did look at recovery factors there. And so that gets more into, yeah. So on this particular one, I was trying to understand how deep we must be going through the multiple layers to get this much water out of these guys. That was another piece of it. And so I was looking at, well, okay, if my frac is contained within the Bakken, you know, and I have this much OIP, it's kind of this wide. And then as I went down, basically my frac XF would get smaller. Anyway, sorry, this is a very long-winded answer. And then as your XF gets, you know, thinner, shorter, you know, my perm went up. And so that was really, I found that was affecting my RF recovery factors more than anything, because of as your perm goes up, your gas goes out, and your, you know, your recovery factor goes down as the gas rail perm starts affecting your oil perm. Sorry, that's a long-winded answer that I wasn't necessarily going to get into, but hopefully that makes sense.
That will have to be a good enough answer for now, Jason. And
okay.
if Yoshi wants to follow up with you, she can do that. But thanks again for a great presentation.
Yeah.
And thanks to Lucas earlier. We're gonna actually skip the break and go straight into Stephen's presentation. A lot of interesting things. So it's good that we've kind of gone through a few of the a little bit of theory, and already visited a few field cases here as well of the multi-FMB now in Vaca Muerta and in the Bakken. And I think what Stephen is going to show will be also very interesting in that or on that note. So Stephen, if you're able to share your presentation, that would be great if he's with us. Let's see here. There we go. And then
perfect.
Perfect. There we go. And it's
up right now.
Yeah, it's.
Can you hear me all right?
Yeah, sounds great. Thank you, sir. So for those of you who don't know Stephen, Stephen is with Devon. By many, at least those of us have been kind of in the gas EOR domain. Stephen is big into gas EOR. Has kind of been the Devon gas EOR person all the way since I met him the first time, to 16, 17 down in San Antonio. But he's also done a lot of RTA work, and I guess officially you are in the Anadarko Basin asset now, Stephen, but you also have, I guess, gas EOR responsibilities. Is that correct?
Yeah, it's a good summary. I don't really know what I do day to day, but I guess I get something done.
Oh, that's great. So, Stephen, he will present on essentially how you can evaluate refracts with multi-phase RTA, and I guess with a special focus on multi-phase FMB, and I'll have a few supporting slides to what Stephen is going to present also just after this. So with that, Stephen, the floor is yours.
Perfect. All right. Well, kind of what I wanted to start off with is, this is certainly, some workflows that are pretty new to us over at Devon. So we're pretty excited about diving into the weeds, and definitely open to, any feedback you guys have, and please reach out, during the presentation, after the presentation, give me a shout directly, and love to talk more about what you guys have seen. So this will be specifically talking about some refracts we've done in the Eagleford. We've done quite a few at this point. Primarily, they are completely new liners that are cemented in place and brand new plug and perf jobs. One thing that's, I don't know, completely unique about the Eagleford, but certainly something that's a big property, is how much our SRV shrinks over time. And so if you kind of live by the CPG MPI life, we can see values greater than even one early time in the life of a well, with significant communication between offsets, and then within a year of production, that's gone all the way down to a 0, and there's no communication whatsoever. So we know that tank that we're draining from shrinks significantly during time, and so we want to see if there was ways that we could try to quantify exactly when and how much that tank is shrinking by. The next thing we wanted to do is see if we could use these techniques to understand how successful our refract was, and how quickly we could figure that out. It's certainly a difficult task to forecast, refract incremental productions using just DCA methodology. So really being able to pull in these new techniques, we're hopeful that that could give us some early time indicators of how successful the refract was. And also, what did we change? Did we just increase, kind of the effective permeability? Did we actually contact new OOIP that we didn't have previously contacted? And how quickly could we figure that out? What I'll say is, if you saw some of our RTEC presentations, we just finished up HFTS 1 Part 3 was in the Eagleford. So we have a whole bunch of new data that we're excited about: permanent fibers, horizontal cores, external, internal gauges, FMIs, all sorts of good stuff. So we've really been able to leverage that to see that, hey, we really are confident in now that we're adding new fractures, we're adding increased OOIP in a lot of these refracts. So being able to tie all this together and now hopefully be able to see it in an RTA space will be fantastic. And then obviously the biggest win is if I can use it even to predict what wells are going to benefit the most from refracts going forward. So the first thing I'll show quickly is just kind of level setting. What does a typical multi-phase F&B plot look like in the Eagleford? So on the left, you're looking at data filtered to just the first 180 days. On the right, you're looking at data that's filtered to 9 years of production, which is close to the total production we have. On this particular well, I went ahead and grabbed one that has had no offset infill or additional activity around it or bashes or anything like that. So the data is quite clean. And what you'll see is the original OOIP that we calculate during kind of the overpressure portion where we're above bubble point is a very significant value of 2 million barrels, and that is pretty common for us to see values in that range. And then going 9 years down the road, very shortly after that single phase period, we get to a value of about 620 million barrels, and we stay on that trend for essentially forever. So you don't ever see, that a typical standard of what people want to see of the multi-phase F&B bending over as you're, going through linear flow until you reach a boundary. We really don't see that because of our OOIP actually has shrunk significantly from what we're draining from day 1 to day 180 to year 1. And then after that, it stays relatively similar, we believe. But you see significant reduction in your contacted OOIP that you're draining from really very quickly. So it's kind of an important note to understand how our production changes when, the first production period when we're draining, frankly, most of our EUR early on in these wells with such high declines, high IPs, comes from a decent sized tank, but then it gets very much significantly smaller as we go. Jumping into the first example of a refract that we've done. As I said, this was a liner. There's no additional activity going on. This is a completely standalone refract here. So beforehand, from DCA, we have a good amount of data on this particular well. This was a fairly early on refrac. So feel pretty reasonable just throwing DCA numbers on there that, hey, before the refrac, we were probably in the world of about 300 MBO. Following the refrac, close to doubling our reserves up to 575. So an incremental multiplier on our EUR of about 1.9x. So extremely successful in adding both significant productivity near term, but also accessing significant amount of new reserves. So I want to see, what does that look like on a multi-phase FMB? And is that a number I can use as a scalar later on for future results? So zooming out once again to the full data set that we have on that same well. The original OIP that we're looking at is about 400 MBO. So this is, the late life OIP that you get from the multi-phase FMB. Like I said, this is a different well than what I showed earlier, but similarly stay on a very straight line. Don't see any of that trending over. And so feel pretty reasonable that there's not a lot of other ways I could have drawn that in late life. And comparing that to late life of the refrac, I get about 790 MBO. So I've seen about an incremental 2 times increase into my late life, if you want to call it, multi-phase FMB OOIP. And that lines up incredibly closely to what my multiplier was for my EUR. So I felt really pretty good that, hey, this is working out. This is doing what you would hope it would do. And our contacted OOIP is translating well to what our total EURs are late in life for both the pre-refrac and the post-refrac case. The biggest win, obviously, though, is if I can use this early on to predict what that performance is going to be. So that was the next step, is let's step back and go to the very early part of this well. So now I'm looking at comparing the super early on data. So I'm looking at the first 90 days here of the original IP of the well and comparing it to the first 30 days of refrac information and seeing something that makes largely good sense with what I saw the last time. So I'm seeing early on in the life of that well, I saw 925 MBO from the slope of the original line. Post refrac, I'm seeing about 1.9 MBO. And so an incremental multiplier of 2.1. So once again, pretty well in that ballpark of what my results were from the actual forecasted DCA EURs. So I was pretty excited about that and hoping that that's something that not just a false indicator of just looking at a small sample set, but it looks like hopefully that's something we can start applying more and more and realizing that, hey, early on in these refracts, as long as you're comparing early life to early life or late life once you have it to late life, they're actually making sense and they're driving together, and we can start using that as more of a predictor for once the wells come online and have just a small amount of data for how much actual reserves am I going to add. Certainly there's the question mark of, did you increase productivity? Without a doubt on this well, it's very easy to, unsurprisingly, yes, I did. I did want to show the numerical RTA side of this quickly just to talk to productivity. I'll say we're still trying to figure out ways that we can use this a little bit more in the refrac world, or just in performance prediction. So certainly open to any conversations people would have, but want to show without a doubt, certainly a significant increase in productivity. And obviously, if you're comparing it to OOIP lines, obviously very much moving up, as you would expect, as we contacted significantly more OIP now than when we had before. So kind of in summary there, certainly with this refrac, without a doubt, significant increase in productivity, significant increase in reserves, and really the early time to late time to actual results seen via DCA forecasting. We really do feel that using this methodology, we may be able to get to a swag fairly quickly on how successful that refrac was, and something we can use to be predictive for our forecasting later on. Another example I'll jump into quickly. I wanted to make sure that I wasn't just convincing myself that this was a process that worked and it was just because I was adding pressure to the system or adding some fluid to the system, and it would always make it look like it was a success and you were contacting more. I went ahead and grabbed one of our refract that, unfortunately, not every refract is a great success. There certainly are some other things at play on this one. But in general, we do have pretty good success with our refracts. But this is one where we did not see much in the way, or really anything in the way of incremental recovery by doing this job. So really, without a doubt, we certainly had an increase in near-term productivity, but in the end, we don't think we added significant reserves. So I wanted to see if that's something that flowed all the way back through the next plot. So I could see that increase in productivity, but see that I'm not going to actually add much in the way of reserves. So here is, once again, similar look of the same plots. This is that late time. So all the data that we do have, which is a significant amount of data for both pre and post refract. And you can see, that late time OIP 480 MBO, post refract up to 530. So just a very, very small increase in what my OIP that I'm contacting is post refract, which very much is in line with what we saw with our EUR and DCA. That this particular refract did not add significant amounts of new OIP that I'm draining on, and thus did not add much in the way of actual EUR. So I felt pretty good about that, but wanted to make sure, same thing of that the pressure is not confusing me, and that's what I'm seeing in early time as well, and it really was. So on the pre-refract side, we were seeing, just shy of 1.1 MBO or million barrels, and similarly post-refract, pretty much right back in that same vein of about that same 1.1 million barrels. So very much in line with what we saw, and we're very excited that, hopefully this is a tool we'll be able to keep using, and it will be able to show us that truly what we added or didn't add. Same vein, we'll click over to the Numerical RTA side quickly. So that, yes, we did increase productivity early on, but it doesn't look like in the long run, probably much in the way of OIP, and it's making sense as well. Although we'll still caveat, very open to anybody's commentary on other ways we could help improve that workflow. The same summary slide that you saw last time, comparing EURs in early time and late time FMB results, but very much in line with what the actual results were. So certainly, we proved up a lot of this work with the recent HFTS, work that we did, and seeing that we truly were, with refracts, able to create new fractures that we didn't have before, able to see that we were not draining very far from those fractures based on the fluid that was left in the core, moving away from prop fractures. And so we knew kind of what that answer was in the back of the book for a lot of these refracts. And without a doubt, we feel that we're now able to show that in an RTA space of really adding significant amounts of contacted OIP on these successful refracts. And certainly it does show the same thing, that our OIP does shrink dramatically. And the timing of that is certainly something we still need to better understand, but going into obviously multi-phase flow is going to make that complicated. So we do not see that multi-phase FMB rolling over, as I've shown before, but we are excited that this multi-phase FMB process does look like it's going to give us a good job of giving predictions for what our pre and post EUR ratio will be, and we'll be able to use that with just a small amount of data to be able to forecast out the results of the refract. With that, I'll go ahead and wrap up. Happy to take any questions. And like I said, please don't hesitate to reach out. If anybody's seen similar things, different things, grab my contact information and give me a shout. I'd appreciate it.
Great, Steven. Thanks a lot. We had a few just question about, is this in the oil window of the Eagle Ford, or can you say something about the context of where it is in the Eagle Ford?
Yeah, absolutely. So these wells varied throughout our position for the two I showed, but for the most part, yes, this is pretty close to black oil. So you can think about it, probably 1,500 GOR, probably 12,000 feet TVD, 0.8 PSI per foot kind of world. So black oil, heavily overpressured, fairly deep.
Excellent.
Probably 300 degrees plus Fahrenheit.
And were these refracts done standalone or executed in tandem with a child well or infill drilling?
So it is a little bit of a confusing story. So the successful refract that I showed first, that was a complete standalone. There was no other operations happening that unit, all the wells have been online for multiple years. And if you go ahead and pull production from the offsetting wells, that production was not stolen from other wells. The other wells really were not affected by those. The second well is a little more confusing. There's a little bit more, there are some other operations going on at the same time that may be part of the reason why you didn't see that benefit, because there were some other infill activity happening. But I think it is gives you a good directional answer still.
Great. And Zach, you had a question here in the chat. Could you just ask that question by audio so I don't misinterpret it?
Yeah, sure. Sorry. Yeah, I was just curious. The behavior there of like seeing a small up or going through TL very quickly looks similar to like what Mo was showing earlier when you have the PDP functionality turned on. And you mentioned that that's part of what you think is going on here is, so I was curious if you tried matching those with the PDP turned on and if that made like the numerical the instantaneous LP slope flatter, or if I misunderstood, if it was already on for all of these.
Yeah, so we did have pressure dependent perm turned on. I believe it was for both matrix and fracture, but I'm not positive on that. Typically, and it's in very similar ranges to what Mo was showing, a 3 to a 4, e to the -4. So we definitely do know that we have significant pressure dependent perm out here. But kind of what Mo was showing, and I'll steal a little bit of Matthias's thunder, probably, with pressure dependent perm, as permeability comes down, it's just going to mask how long OOIP takes to roll over. So you would expect that even with pressure dependent perm, that you would eventually see, 9 years is a pretty good amount of production life. And I have some wells that go even longer and still show the same character. So we do know that it's something more than just a permeability reduction if we're not ever seeing that OOIP ever recover. So it is, not just getting tighter and tighter, but still able to flow. It is completely closing off of those fracture tips and getting shorter and shorter fracture half lengths.
Okay, thank you.
Absolutely.
That is a great question, and it's just like some of the cases that Mo showed as well with fairly significant pressure dependent perm here. You would see it bend eventually. It would just take a little bit longer time. But as Steven says here, this is basically the same line, and it's been on that line for 9-10 years, which is almost 3,000 days or so. So that is good. There is one other question. Curtis, you have another question here?
Yeah, just a real quick one. Can you hear me okay?
Yep, I got you.
Great. Yeah. How much, let's say, comfort level or feeling of using the complete PVT description, multi-phase flow, in other words, with the numerical RTA and the multi-phase flowing material balance, having all that consistency in these, complex fluid multi-phase systems where GORs, I guess, are climbing over time. I mean, versus using just your standard RTA kind of workflow. I mean, can you just comment on it? Not saying, well, it's much better. I mean, what are some of the takeaways that you like in using these methods that have all this consistency on the PVT multi-phase flow part?
Yeah, absolutely. So I guess kind of the first comment I'll make is the Eagleford, particularly our portion of the Eagleford. We're blessed, and kind of, frankly, some of the pressure dependent permeability conversations hit on it a little bit. We do not see massive rises in GOR as we pass through the bubble point. And we certainly have a lot of headroom here, probably 6,000 pounds of headroom. So it takes us a while before we get through bubble point. And then we don't see significant rises, likely due to how tight our permeability is directly right around our fractures. So we don't see huge pressure swings in those cells. So we are benefited a little bit by that. So that some of the analytical methods are okay here. But what I'll say is we have never been able to get reasonable matches on our OIPs even in that workspace, even despite not having massive changes in our properties. So this is what, the first time we're really starting to see values that make a lot more sense, and not seeing super false end of linear flows due to a little bit of that GOR behavior. So yeah, certainly new in the process, like I mentioned, but really liking what we're seeing so far. And credit to you guys as well. We do have your equation of states for the Eagleford, which has helped us out a lot. Also on being able to get a lot more wells through the system quickly and having confidence in the data that we're putting through.
Very good.
So it's really the consistency and less of the uncertainty on that side of it. You can think about other issues that you have to deal with.
I think yes, consistency going well to well to well has been a significant benefit for us. Yeah, absolutely.
Good. So we have one last question, and then I think we need to jump to the next presentation. And that's just a quick question from Yoshi about the drawdown profile before and after the refract for that standalone well. And maybe you can comment on also, like, very interesting thing when you do a refract is, are you actually getting similar bottom pressure as the virgin reservoir pressure, or are you getting kind of something more similar to the old? And that's also a way for you to diagnose whether you're doing something correct or not.
Yeah, absolutely. I don't think I have any slides on here that'll actually show pressure, but you'll see we get to very similar IPs pre and post refract. I'll say we are, the Eagleford in general is relatively, purposely cautious on what our drawdown strategy is. And we can get to very, very high IPs, but we also have very steep declines. So frankly, the NPV of getting aggressive isn't that great. We do typically see in a lot of these refracts, especially the more successful ones, we see us getting back up to virgin pressure when we turn these wells online. So certainly another indicator that we're accessing reserves that we were never accessing before due to issues with such wide cluster spacing that is just never draining between those fractures. So we do get close to virgin pressure. It certainly does draw down typically a little bit quicker, but we do use a pretty similar choke strategy. So probably the total drawdown is a little bit faster on a post refract than the original well, just because of typically having more contacted new virgin rock on the original life of the well. But the strategy from a choke management standpoint looks relatively similar. I'm not the expert on that. Sarah Bacho on my team is certainly far more familiar with everything. So if anybody wants more detail, I'm happy to connect you up with her and she can help out as well.
Perfect. No, great stuff, Stephen. I'll just do a quick follow-up to this, and then we'll jump into Tyler's presentations and Steve's presentation. We have to skip the break now just to make sure that we get through everything. But it's essentially just to build upon some of Stephen's points here. So I'll just go ahead and share real quick. And it's related to the problem statement that Stephen mentioned, that in some basins we see that there's field evidence that suggests that the fractures are closing as we deplete the reservoir. And what does that mean? Well, it means that it's not a permeability reduction, but it's essentially, or if it is a permeability reduction, that permeability goes to zero. So it will be parts of the reservoir that close off in terms of production, and essentially OIP is reducing with time, which is the example that Stephen just showed. And how will that impact multi-phase FMB? So just to show that with a simulated case, we ran a case where all the fractures are open, and then we had just a very simple comparison case where the fractures are actually closing with time. So they're reducing with time. The OIP in both the cases are the same, but the case number B, eventually over time, gradually 70% of the fracture area is closing over time. And then we'll just compare and see how it looks like in the multi-phase FMB. And you all know in the multi-phase FMB, we've gone through this many times, but the diagnostic plot is very simple. Inverse of that slope gives us the pore volume. But important to remember in this context is, especially for the cases that Stephen showed, is we'll have these three key periods. The period 1, which is where also Jason talked about earlier, and also Lucas and Vaca Muerta, where there's basically oil and water primarily. We call it single phase because there's no gas coming out of solution. So that's why the bottom hole pressure is higher than the saturation pressure. And then the second period is the transition period where gas is coming into the system, and this higher compressible gas is causing a transition period which will yield a shallower slope for a period of time before that also stabilizes into a third period. And if everything is consistent, both of these slope, or if you've seen the entire pore volume that you're contacting in while you're in single phase flow, these two curves should be the exact same curves. So just to show that in a simple case, if we have a case where the oil in place is 3.7 million barrels, these are the simulated results versus time for that. And we do the multi-phase FMB plot, then we see that the slope before you go two-phase and the slope after we go two-phase both yield the same oil in place. So that is consistent, and that's what you should expect if you don't lose oil in place over time. If you bring this into a numerical RTA exercise, the numerical RTA exercise will provide you with a spot-on result for oil in place and also LFP for this well, where we know the inputs. Case number B is this case where we're actually we're losing production over time. So 70% of the fractures gradually close with time, and this production data looks like this. And just to compare that to case number A, you'll see that case B, where we're losing production gradually over time, yields after 1,000 days 600,000 barrels versus 900. So about a 30% decrease in production, or 50% decrease in production. If you do the same exercise for this well, when it comes to multi-phase FMB, you'll see that the early time slope is yielding an oil in place of 3.7 million barrels, while the late time slope will never actually get to a oil in place that is the same as the initial slope. In this case, it's giving us 1.9 million barrels. And this is exactly what Stephen has showed already in the previous slides. If you bring this into a numerical RTA exercise, you'll see that you'll hug the correct oil in place line initially, but then it will actually cross through different stems and in the end go through a stem that is much or has an associated OIP that's smaller. So in this case, without doing anything actively with your numerical model, it's not easy to account for this. You'll see it and you'll observe it in the numerical RTA workflow, but you won't account for it unless you do something very, very particular. And the way we created these models were just to have a model controlled on a flowing bottom hole pressure, and then we simply created a case with 100 fractures, and then we just shut off those fractures gradually from 100 fractures to 30 over time. What should be emphasized, though, is like the other extreme that, or the question also from Zach about pressure-dependent permeability, is that it will have a very similar signature on the multi-phase FMB plot, that you'll have a first slope that suggests a high OIP and a smaller slope that will come late time. So the shape will be similar, but eventually you should, with the pressure-dependent perm, come onto the correct slope late in time, which you didn't see in the field data from Stephen. But just remember that the shape will be the same. The last point that I'll make before I'll bring it over to Tyler is just using multi-phase FMB for a refract example, and that it actually works very well for that as well. Here you have a simulated case where we're just doing a refract after 200 days, and we're just doubling the accessed pore volume after 200 days. And what is happening with your multi-phase FMB is that your first slope will yield correct oil in place after 200 days, and then when we are doing the refract, we're getting the the correct oil in place after the refract as well, which is 2x of the first one in this synthetic example. So we know that works. And if you bring that into a numerical RTA workflow, what you'll see if you use the cumulative switch in that the numerical RTA plot, the Bowie diagnostic plot, the cums will start to increase, and you'll see the same in the instantaneous, so that your LFPs will basically just increase at that point in time. So nothing more magical than that. Very good. So on that point, we'll just go over to Tyler's presentation. Is this there we go? Perfect. And there, so that's going to be just a presentation on touch upon some of the probabilistics and how Tyler has used that internally. So with that, I'll just leave the floor to you, Tyler. Can you just confirm that the sound is, there we go, sound is perfect as well. So for those, excellent. So for those of you who don't know Tyler, first time I met you was back in Florida before COVID. Good memories on the Saga conference there. He's with Taprock, was with Taprock also at the time. I'm sure. I know at least the first thing I heard about you, Tyler, was that you were a very good presenter, and I remember I really enjoyed your presentation back there in Florida, even though the technical topic was not a topic I knew anything about. So really looking forward to this one, and I'll just mute myself and turn off my camera.
Okay, sounds great. So I'm Tyler McKelly with Taprock Resources. We are an independent operator in the Delaware Basin in the U.S. And man, our reservoirs are a lot of fun because we have primarily the Wolfcamp, but we have maybe 7 to 8 different primary reservoir units that can be anywhere from 100 feet thick to 400 to 500 feet thick. And then we're over a gross column of up to 5,000 feet. And we span anything with GOR from 800 all the way up to 5,000, and it provides for a pretty complex reservoir system to evaluate. And I want to talk here about how we're using the multi-phase workflow to inform some of our activities here through the probabilistic sensitivities. And there we go. So we're working in the exploration and also actively acquiring assets. In exploration outside of the primary Wolfcamp, we're looking for different horizons, and with acquisitions, we're looking at geographic extents that are outside the core of the basin or sometimes within the core of the basin. So we're using numerical RTA. Here's the standard plots we're used to seeing. And what I'm generally working with is FCDs that are much lower than the infinite conductivity that we've been told to use in the Apache papers. I'm looking at a FCD of 1 to 5. And when we're in our higher nanodarcy reservoirs, the 1,000 plus nanodarcy, we sometimes go up to 5,000 to 6,000 nanodarcy. And then I'm finding better matches within our system with a 10 to 20 FCD or plus, since we're relatively infinitely conductive there, when we're in the 100 to 1,000 nanodarcy. So some of our tighter rock. We have some rock that's tighter than 100, but generally we're within 100 to 1,000. And that's just helping me get a better match on that numerical system. And then one of the other challenges that I'm being presented with presently is matching the GOR in our thick, so 200 plus foot thick reservoirs, primarily when they're volatile oil. So when we're dealing with 3,000 GOR plus, I'm having some difficulty within our numerical RTA and matching that. It's possibly a mixed system. It could also be because it's not just a single homogeneous reservoir unit. We're dealing with some sands, some shales, some interbedded systems, which I'm very much looking forward to the new Whitson update with the multi-layered system. And then we go from numerical RTA to numerical simulation. Of course, everybody here should be familiar with this workflow by now. How I'm using it is my objective is to find our economic failure conditions. So GOR and its impact on takeaway capacity can influence that quite a bit because our takeaway capacity could curtail our peak oil rates. And then water oil ratio, it's loose tie to petrophysical water saturation and that impact it has on LOE. So brief comment on the petrophysical water saturation. Sometimes we'll have a water saturation of 40%, but the water oil ratio, producing water oil ratio will be 6 or 7 to 1. Other times we'll have a water saturation of 70%, but it's a 1-to-1 water to oil ratio. We're currently talking with our petrophysicist and some other geologic people to assess why that's happening. And one of the primary drivers we believe is maturity, and what is registering as oil rich might not actually be mobile oil that's able to move through the system. So that's been a tricky component where I have the water saturation from our geologist and I can't really plug it into the system. I'm really driving it more off of what our effective producing water oil ratio is. And then influence of any of these other variables. So as I mentioned, water saturation, but we also have porosity, the fracture height, the reservoir thickness, FCD, XF, and the number of fractures. I'm going to present here in a moment the number of fractures and the cluster spacing and the impact that that has on our ultimate economics. But any of these variables, as you're well aware, can really drive what's going to happen with your program. So holding all of their variables constant, when we go into the numerical model, I varied here just our storage component, the porosity in this case, and I've taken a 4 to 7% uniform distribution, and you can see the colors here: green oil, water is in blue, and oil or gas is in red. And from that P90 to P10 spread, there's maybe a plus or minus 15% spread here from the P50. So that's a pretty substantial swing just by varying porosity a few percentage points. Or if we go to the connection, our frac height within that reservoir system, 150 to 250 foot uniform distribution in that frac height gives us a 20 to 25% spread in that P90 to P10 from our P50 number. So we could go anywhere from 300,000 barrels to close to 500,000 barrels. You can imagine that ultimate recovery is going to drive your economics pretty substantially. However, thickness of the reservoir height, at least with this permeability that we ran, which is 600 to 800 nanodarcies, and as we saw in an earlier presentation, until we get above roughly 1,000 nanodarcies, we're not really getting contribution outside the frac tips, either in length or in height. And so in this case, we see that the impact on the ultimate recovery on oil is maybe 2 to 3% swing. Water, it's pretty insignificant. In gas, it's almost nothing. These are all individual cases or individual variables that I've run the sensitivities on. I like to start on that and do singular variables rather than combining storage, connection, and thickness all in one, because that's tends to be a pretty difficult model to assess. One thing on permeability, for example, I don't have it shown here, but permeability doesn't ultimately affect, except for maybe a very big reservoir unit with high permeability, doesn't affect our ultimate EUR, but it very much affects the drainage rate, our acceleration. And in a commodity price environment like we're dealing with now, that drilling our high permeability stuff might be more favorable if we can. But out of all these simulations, we get our oil, water, and gas rates, we get our recoveries, the distributions of P50, P90, P10. But none of that really tells me how much money we're spending to put this stuff into the ground and what is our ultimate economic output from that. And that's where I take these numbers and we'll run it through from the Numerical RTA down into our simulation and ultimately into economics. And here's just an example of cluster sensitivity, cluster spacing, and the sensitivity of the PV10 to various cluster spacing. And I have the 30-year plot in the background, and then focused here on the end of the period. We can see that years 29 to 30, and the numbers here are feet. So the lowest number here, 10-foot cluster spacing, ends up being the worst performer on a PV10 basis, which makes sense. If you look back here, it's kind of hard to tell here, but we spent the most money. We spent almost $9 million in this hypothetical case to tighten up cluster spacing, to put 4 times more clusters from the 40-foot case, to put that into the ground. So you dig the deepest hole, and you're accelerating very quickly, and you get a lot of recovery in the blue, but ultimately your return on investment is just not that great. Whereas you have a collection up here between 20, 15, 25 feet cluster spacing that ends up being roughly the same PV10. They're within $1 million or $2 million of one another, or sorry, $100,000 to $200,000 of one another, which would tell us that for this given reservoir system, this given permeability, thickness, frac design, effective pounds per cluster, effective feet per cluster, we could go with a little more acceleration at 15 foot, and ultimately in 30 years it might be a wash, but maybe we take a gamble on the commodity price that we're working with right now to try and eke out an additional incremental PV10 on those dollars. So this is just an example on cluster spacing of the 6 sensitivities that can be run to see the ultimate economic outcome. We could do this, of course, with XF and to say we have a frac model. And is it worth it to put in 50,000 pounds per cluster or 20% more at 60,000 pounds per cluster? So having this numerical RTA workflow to history match and then to really expediently run a number of sensitivities, we're not having to go into CMG. CMG is great, but the amount of time that's required for us to spin up a CMG model and the resources and the expertise, it's been great to do it in the Whitson Plus package. And yeah, it's a lot of fun. So that's the pretty short presentation that I have there of how we're taking numerical RTA through the simulation into tying into our economics. Really wanted to convey these ideas and show you some of the end of the workflow that I've been learning so much from other people about, the intricacies of how FCD impacts our work, for example. So it's been a lot of fun being part of this consortium.
Right. Just on a couple of questions here, Tyler. The first one just related to the distribution. So one question from Yoshi is used a uniform distribution. Was there a particular reason for that, or can you elaborate a little bit on why uniform and not? I think there's 4 different options probably in the software, like triangular and uniform and normal, but
Yeah. We could run a normal, we could run a triangular distribution. The reason I chose to run uniform in this case is that I wanted to give 4% for porosity, for example. I wanted to give the 4% and 7% equal opportunities to be run in this model, that I don't want to pretend to have any more certainty or control over the subsurface. And I don't want to center in on 5% and say it's a normal distribution from 5%. So for these first scoping passes, because there is so much uncertainty in our data, I'm just going to put it on a broad range, because I'm more interested in the bookends, so to speak, that I really don't know exactly where that P50 is going to be. I want to know on my lower bound, what is my P90, where are my failure cases relative to that P90 in these simulations, and am I clearly all my likely porosities are going to be 5% and above, and my failure is at 3%. So it's the uniforms just so that I touch that lower end with as many cases as I touch the upper end.
Great. The other case, when you for the economics there, did you run like the price deck that you run in the background? Because you talked about acceleration in this price environment. Maybe we're not seeing these prices forever. Did you was there some kind of did you build that into the analysis here, or can you elaborate on that?
Sure. Yeah. Entirely other layer that can be run with this. This is just it's a singular model that it's a flat price deck. I forget exactly what this one's, probably 65 and 3, which is completely blown out of the water now. I've run recent ones at 106 or 107, $100 per barrel and $7 gas. That does change the economic outlook. It'll certainly push this PV10 up quite a bit, and it can affect what cluster spacing is optimum for this given environment. And we can run strips or really any type of price deck that we want to do. And we tend to do that. We have our own internal flat decks and hedge books, what we're running off of that. So not shown here, but that is certainly something to take into account, is that I'll take the reservoir piece. We have the rock, we have what we did to the rock, our frac design. I want to run the sensitivities on that frac design, just like I ran sensitivities on the geology. And then that final piece is to take our cases from the completions and run the sensitivities on the economics, because we are never correct. We're not ever exactly right. And I want to know for the different commodity prices, if I chose 15-foot cluster spacing out of this example shown here, is there a price environment where that becomes no longer the best decision and I should have gone with 25 or 30-foot cluster spacing? And we'll use that to guide our discussions about where we think commodities are today versus where they'll be in 3 years, which is a crystal ball. But that's a great question. Yes, price decks are another dimension on this analysis.
Yeah. Oh, great. Yeah. So thanks a lot, Tyler, for showing this. Really insightful, and you're very good at explaining a lot of things with a few words on the slides, and that is always enjoyable as well. With that, I think we're ready for the last presentation for today. It's actually a presentation that we've been requested from many folks in the consortium from multiple different angles, actually, and that's based on a paper that Steve from which at the time he was with Newfield, and then he was with Cimerex, or what's now Quotera. So we took the chance and invited Steve as a guest speaker for this last part of today, just on how to use flowback data to estimate initial reservoir pressure. So I think that would be a great way to end the session today with all of you. And for those of you who don't know Steve, Steve has been active in the technical domain for years now, and was, as I said, with the Newfield and Cimerex, and very known. And I heard many times actually last week as well, referencing to your GOR paper there as well, Steve, which has been used and referenced by many. And I think you probably mentioned it before as well, that the reason why a lot of people like it is that it's not too many equations. But great. So the floor is yours, Steve, and thanks again for joining us here today.
Okay, thank you, Matthias. Can you see my screen?
Yep, that's perfect.
Okay. And so this is like he said, is a blast from the past, from 2014, 8 years ago, during the days when bottom hole pressure gauges were rare for flowing data. And I want to mention who the co-authors were: Brian Ponnell and Jared Franke, who were both with Newfield at that time. I'm going to show you a couple of examples. They're from this central Oklahoma area, from the Stack, which is Woodford and Merrimack, and the Scoop, which is primarily, at that time, was just Woodford. And that's where the examples will be from. And I've got the Newfield logo here just for nostalgia's sake. So I'll show you a few of these plots. The way we came up with this method was just watching hourly flowback data on a lot of wells as we were drilling and trying to understand what reservoir pressures were. We didn't have very many defits at that time. They were pretty rare. But what I'll show you on these plots is the black line is bottom hole flowing pressure on the left-hand axis. On the x-axis, we've got days of flowback. This is from the time we open the well after the frac and start flowing. So there's a water rate on the left axis, an oil rate on the left axis, the gas rate also on the left axis, and then the casing pressure on the left axis, and also the choke opening on some of these plots, which is on the right. So what we were doing is calculating an estimated bottom hole flowing pressure from surface data, which is just, as you know, the surface pressure plus the hydrostatic head minus the friction pressure. And that's fairly straightforward for water only. But as you get into multi-phase flow, there can be a lot of uncertainties involved there. So on all these cases, we were flowing up casing, no tubing in the hole, and no flowing bottom hole pressure gauge. And we noticed as a similar pattern on all these wells, both Woodford and Merrimack. We had a period of water only flow in both of these formations, which is something that I have not seen in the Wolfcamp in the Delaware Basin, for example. So you have to use a somewhat different method there. But in both of these cases, we had a water only flow period, which we knew was starting out at a bottom hole pressure well above reservoir pressure and falling until a point where it leveled out here and you started getting traces of oil and gas coming in the well. which we interpreted to be the reservoir pressure or slightly below the reservoir pressure because we had enough drawdown to start getting some hydrocarbons in the well. You'll notice in this example that the first measured gas is about 1.7 million cubic feet per day. Well, obviously, the gas didn't start flowing all of a sudden at 1.7 million. That's just when we started measuring it. So that's really the reason for the flattening of the casing pressure, is because we were getting traces of gas coming in the well, lightening that fluid column. So this bottom hole flowing pressure becomes erroneous during the time when you're producing some gas but not accounting for it in your multi-phase flow correlations. So basically the method that we came up with was to identify this flattening in estimated flowing bottom hole pressure and say that that's roughly where our reservoir pressure is, because we knew the flattening was due to the fact that we had trace amounts of hydrocarbons coming into the well, which indicates we've got to be down to reservoir pressure in order for that to happen. So that's the basic idea behind the method. So if you don't have that initial period of water only flow, and you're really starting at this point where you have first measured hydrocarbon, you can estimate a bottom hole flowing pressure there, but you know that's going to be slightly below the reservoir pressure because you've got, in this case, enough drawdown to produce 1.7 million a day. And this would have been from a 5,000 foot well. But a lot of times that's all you have if there's no water only period prior to that. So what's actually happening, as I mentioned before, is you're getting trace amounts of hydrocarbons entering earlier. And so your actual bottom hole flowing pressure probably looks more like, a continuous decline, and your actual gas production is increasing from 0 up to where you first start measuring it. So that's why we use the flattening area as an estimate of reservoir pressure. Now here's another example, just a different well down in the scoop, also in the gas condensate area. And in this case, and we saw this a lot of times, is that the casing pressure will start increasing as you get more and more gas coming in, lightening that fluid column. And what's actually happening, of course, is that your bottom hole flowing pressure continues to decline, but you're not accounting for hydrocarbon in your calculation of flowing bottom hole pressure. And so in that case, you would use the minimum estimated bottom hole flowing pressure as your reservoir pressure. Just one more example. This is a stacked Merrimack oil well. And you'll notice pressures are considerably lower here in the Merrimack because it's shallower. We still have that water only period, in this case about 4 or 5 days. And we estimated the reservoir pressure at about 4,400 psi. So really a very simple method. But again, if you were to use first hydrocarbon production as your estimate of reservoir pressure, you'd get something like 3,500, which we know would be too low. Some of the early data that we put together showed a good correlation between DFITs and this estimate from flowback data. Now, I've seen other areas where the correlation is not as good. So it's important whenever you're applying this method to make sure you are actually getting a good correlation with reservoir pressures measured in a more accurate or more traditional way. One of the things we were able to do using this method was get an idea of how much the reservoir pressure varies across the field, because we could use this method on every well with no additional cost for bottom hole pressure gauges or any other instrumentation. And in this particular map of the scoop, each of these large squares is a township. And we were able to show that the reservoir pressure varies from about 0.6 psi per foot, the reservoir pressure gradient on the west side, over to about 0.46 psi per foot on the east side, simply from using this flowback method. So that became very useful to us in all our analysis where initial reservoir pressure was needed. So as I mentioned, if you don't have any water only period, then you can use bottom hole flowing pressure at first hydrocarbon. And actually, you know, this is going to happen if the well is shut in for quite a while after the frac before you start flowback. The frac charge will bleed off and the hydrocarbons will migrate into the fractures. And really, using this in the Wolf camp, just the bottom hole flowing pressure at first hydrocarbon, we found that was really close to the defits that we measured. There wasn't a big difference there, as we saw in the examples I showed you here from the scoop and the stack, from just using bottom hole flowing pressure at first hydrocarbon. One of the other issues is that you do raise the reservoir pressure locally around the fractures by all the fluid that you pump in, of course. And we did see that when we went to much larger fracs than the Woodford, we were getting higher initial reservoir pressure estimates by using this method. So how fast that frac charge leaks off and how long the well is shut in can affect the reservoir pressure that you're getting from this method. And then one of the biggest issues that I've seen in recent years is that as we begin drilling infills, where we're not dealing with just parent wells, but wells that communicate with each other, is that these frac networks can all be connected. And if you're trying to estimate reservoir pressure from pressures in an individual well, you have to be aware that that pressure is very much affected by any other frac networks that it contacts. And in particular, if you've got a parent well and that frac network of all the infills has fracked into that parent well depleted area, that parent drainage volume is going to very quickly suck a lot of fluid out of the new infill area, and you'll get a lower pressure in that entire frac network. So we found that defits are still necessary. Even if you have bottom hole pressure gauges in every well, you can be misled as to what the local, or in other words, point measurements of reservoir pressure really is if you're dealing with connected frac networks. So defits are still very useful, even if you have bottom hole pressure gauges in every well when you begin flowing. And that's really all I have to present. I'd be glad to answer any questions.
Excellent, Steve. So just like like in your experience, defits, you know, how many wells of the sample sets would you say that you have that on? Because that's something you probably have on a very small subset of wells, right? So can you use some of those learnings to wells where you either only have gauge pressures or bottom hole pressures, and how would you, or calculate bottom hole pressures, and how would you use those learnings for those wells, I guess?
Sure. Yeah. Well, yeah, that's what we typically have, is not very many defits compared to bottom hole pressure measurements, or using this method where you're doing it from surface pressure. But yeah, the key is how good is your correlation between other methods and defits, and especially if you've got depleted areas that you're connecting to. Like I mentioned, it's you really need those defits in localized areas to validate whatever. Does that get to your question, Matthias?
And I think another question we had very related to this in the last knowledge sharing session we had was this whole, you know, if you have a parent well and you drill child wells and you calculate bottom hole pressures, or you measure them with gauge pressures, should you apply the same or similar initial pressure for the children wells, or should you use whatever the gauge pressures are kind of saying or providing you with in terms of values? And do you have like what would you do if you did modeling for a pad and a wide range of wells where you knew that there was significant depletion in some of children wells, would you still use the same or something close to the initial PI or something else?
Well, yeah, I mean, you'll have to go through that process in every different area, but yeah, I can say that we found that bottom hole pressures that we measured in connected frac networks were typically lower than what the virgin pressure was, and we couldn't believe, sometimes that was over half a mile away when you've got a string of connected infill wells and the whole frac network is being drawn down by that depleted area around the parent wells. You have to make some estimate of what the actual initial matrix pressure was around those infills. And the conclusion I came to was that you do need some defits in those areas, in places that are far enough away from the parent before you frac all those wells and connect the whole frac network. So yeah, we did make an estimate of what the actual initial reservoir pressure was based more on field averages and how far we were from the parents rather than using actual pressures in infill patterns.
Okay, very good. Any other questions at this point, or any comments from Curtis or Mo?
Yeah, thanks, Steve, for the presentation. I really enjoyed every single time I hear it. Can you go back to slide 8 for a second? One of the things that I noticed on the 1-to-1 line is that the initial pressure estimation from Flowback is consistently higher than that of the DFIT. Did you guys use a correlation coefficient of some sort in order to bring your initial pressure down to where the DFIT would be? And I guess, what do you think would be causing the estimate to be higher, if there's anything more than just the frac charge aspect of it?
Yeah, well, for one thing, I don't, this is a small number of data points, and I've seen it go the other way too. Especially if you have to use pressure at first hydrocarbon to estimate your reservoir pressure, that would make everything fall below the line probably. And the way we did DFITs back then was not exactly the way we do them now, and the way we interpret them is different as well. So, I'm reluctant to really generalize about making some correction to all the points for that. But you make a good point. If you're seeing a systematic variation, it makes sense to adjust your estimates accordingly.
Nice. And I guess I just had one more additional question, which was around the chemicals that we pump. Oftentimes, actually, every time we'll pump a friction reducer, and friction reducer contains a lot of surfactants. How do you think that impacts? Do you think that would be that would allow for a lot more free gas in the system and elevate the initial reservoir pressure? And what are your thoughts around that?
Okay, are you talking about a gas system? You're talking about a gas system or an oil system?
Yeah, basically from wet gas, essentially all the way across to black oil, but essentially in the gas condensate system. Because surfactants lead to wettability changes in the rock, which would allow for more free gas. So I'm kind of curious if you think that would increase the pressure estimate from Flowback as well.
Yeah, no, I tend to think that the reservoir is going to give up what's flowing at a farther distance from the fractures that's not necessarily influenced by those surfactants. So your wettability alteration is going to be, pretty limited. But I wouldn't, on the whole, I would say no, that probably doesn't have a big effect. And I have seen wells that we frack with surfactant and without surfactant, didn't see a significant difference in the gas water ratios or oil water ratios in those cases. But you could have in a certain rock that's more sensitive, you may see an effect there, but I haven't seen that.
Gotcha. Thank you so much for the knowledge. I really appreciate it, Steve.
Thank you.
Great stuff. So I see we have 1 more minute, and I think we'll just wrap it up there. So we have a perfect 4-hour session. Thanks to all the speakers today, and also, of course, thanks to you there, Steve, for the guest presentation as well. The presentation will be, or the presentations will be provided as a follow-up to this session, and also the recordings will be distributed as well to the participants in the JIP. So if you have any colleagues that you'd like to share some of this with, that should also be doable. So with that, we'd like to just thank everyone and wish everyone a good rest of the week. And when the 4th of July weekend comes, also enjoy that. So thanks again.
Thanks, everyone.